We are live.
We are live, right? Okay. Yeah, I think Amritanshu sir, we can start.
So, good afternoon, India. This is Amritanshu Vajpayee. I wholeheartedly welcome you all on behalf of Indian space industries exhibitors and all the allied knowledge partners to the second day of the ongoing National Technology Day celebrations of 2021 under the theme of Advanced Technologies and Applications in Engineering. As we all know that yesterday on the inaugural day of this quadrennial session that our organizations are organizing, we had a very wonderful three lecture series given by Mr. Manoj Jain, Dr. U. Chandrasekhar, and Mr. Achankya Huddar on the different aspects of the 3D printing and the allied sciences. So, continuing on the same pattern, I welcome you all to the second day of this very same workshop, or you can say the webinar series that Indian Space Industries Exhibitors has organized under the leadership of the Managing Director, Shri A.C. Mathur sir. And I welcome all the organizers, all the knowledge partners on behalf of ISIE. Today, we shall be going through a very panoramic view of the applications of the 3D printing in space habitats by the first speaker of the day, Mr. Shashank Shekhar. That will be followed by a presentation by one of the students, Mr. Pankaj Kumar, to be followed by inflatable structures and materials technology in India session by Dr. Sanjay Upadhyay, and the concluding session shall be taken up by Dr. Bishak Bhattacharya from IIT Kanpur, who shall be giving his lecture session on smart materials and systems technology in India. And all the people who are really interested to gain more and more on this knowledge forum and to interact with all the speakers are requested to kindly put in their questions over the YouTube chat box. The technical team that of ISIE that shall be monitoring the chat box will take care that your queries they do come up in front of the speakers. With these words, I hand over the reins to the host of the day, Shri Chintamani Pai from Space Geeks Mumbai. Welcome, Chintamani sir. Welcome to the session of the day.
Thank you, Amritanshu. It's my pleasure to introduce our session speaker today, who is going to take us on the journey of 3D printing. Um, it's a great pleasure to introduce him. So, Mr. Shashank Shekhar is currently CEO at Mycop Private Limited, and Mycop Private Limited provides 3D concrete printing solutions to various sectors like architecture, inf- infrastructure, and housing. Mr. Shashank did his BTech in the civil engineering branch from IIT Roorkee in the year 2012 and then joined Jindal Steel. He left Jindal Steel in the year 2015 to do PhD in the field of 3D concrete printing at IIT Gandhinagar. And with that, I request Mr. Shashank Shekhar to take over and take us to a journey of 3D printing.
Thank you, Chintamani. Thank you, Amritanshu. And special thank you to Mathur sir. So let me start with this talk. Yeah. I hope you can see the presentation.
Yeah.
So 3D printing also has touched like construction sector in past decade a lot. So if we look at the construction sector, so let's first discuss about construction at Earth, then we'll go beyond in space. So if we look at conventional construction practice, so it is very time consuming, labor intensive, and difficult to do like construction in tough terrains. And this is mostly done using formworks, like which are made of wood or metal and all. So there is limited design freedom as well. So now to like remove some of these challenges, 3D printing has come into like a construction sector, and in past 10 years, it has made significant progress as well. So this is basically a layer by layer manufacturing process. This could be powder bed or this could be extrusion based as well. Here formwork is not required, and we can actually directly just do printing from a CAD file, which is first sliced as in other 3D printing method. And then we can use this G code to just pour the specially designed concrete layer by layer. So here it is very important that the concrete or the material which is deposited gains strength very fast. Otherwise, it would collapse under its own weight. And we are talking about like printing 3 meters in an hour. So it's not like we are going to print 30 grams per hour like in usual plastic or metal printing. Here we are talking about 3 tons of material per hour. So that is the scale of 3D concrete printing or printing for construction, because even this 3 tons per hour is actually small for regular construction. In regular construction, we want like 15 tons, 20 tons per hour output. So still this technology is evolving. People have demonstrated like this can be used for small bridges. You can see the shelter which actually was printed by us in the top center area. We have also demonstrated that bunker can be done. People are doing a lot of work on regenerating the coral reefs using this technology because they can use the very complex shapes. Infrastructure is also there, and furniture, architecture, facade. So a lot of things can be possible using 3D concrete printing technology. So this is basically done using extrusion type method where the layer is deposited using an extruder or a pump layer by layer in 3 dimension. But if you want to go more complex, then powder bed method is used, where a large bed of cement sand mixture is placed, and then we pour liquid on a specified location as per the CAD file, and then you can do very complex shapes. So earlier was the extrusion bed method and extrusion based method. This is like powder bed concrete printing, where you can do very complex shapes very precisely. But here the challenge is that the output is like more than 5 times smaller compared to the extrusion bed method. So this has very limited applications as well, because also the strength is very limited in these kind of powder bed technology in concrete printing application. So far we have developed a large scale gantry, which is like 2.5 meter by 2 meter by 1.5 meter in printing volume. We can print like very high strength concrete composites like up to 35 MPa. So to comparing it with a normal construction, so normal house are built using 20 to 25 MPa concrete columns. So this is a high strength concrete mix because we are using a higher cement content, because this is mostly in very fluid form. So it's more makes sense to actually go for higher strength. Also, it can give a good output, and the power consumption is very small compared to a normal construction practices. And this is very easy to scale. We actually are going to scale this facility to a very large printing area. So there we would be printing like entire bunker like just in half a day. So that's the scale that we are talking about. And this facility should be commissioned in by this coming June. Let's see if COVID does not hamper us a lot, then we should be actually able to have this facility in near SG Highway. So you will be welcome to visit this. So this would be amongst the largest 3D concrete printing facility in world. We have developed a lot of product portfolio using concrete printing so far, like furniture we have developed, and we have like shown it to various agencies. Even Indian Army visited our facility, and then they saw that this is something good. So then we went on to make bunkers for them, like shelters, habitats. So these are some projects we have done on Earth. So let's see how far we can go in terms of lunar or Martian missions. So basically, this project was done in like parts. So we printed segments, small segments, then erected them using cranes, and then we integrated them vertically using the vertical reinforcement like angles and rebars, and then fill the hollow core using the local soil to make it more cost effective than put the roof and then all. And also at the end, this has to become viable in terms of economy, in terms of sustainability. So we had a comparison where we see that the cost is like very comparable to normal conventional construction method. And the advantage here is that the time and speed of the construction. So compared to normal construction practices, this can be like 4 to 5 times rapid compared to that. Like a normal masonry habitat like that would have taken us around 3 to 4 weeks. However, we completed in like just 2 days. Also, we can now go very complex in design. We can integrate like voids for better thermal insulation. And because of those voids, we were actually able to achieve a very lesser quantity of material required. Like the material requirement was reduced to half, and we were able to achieve a very good thermal insulation as well. So other applications are also in pipeline for for various clients like Indian Army, CPWD as well. So we are hoping to develop these kind of projects soon, like for sentry room, guard room, habitats, rapid shelters as well. So these have certain advantages in terms of when comparing with the normal construction practice, because time is a major factor. The labor required reduces a lot, and we have a good thermal comfort insulation as well. And at the end, the cost is also very comparable to the conventional construction method. So we are hoping that this technology would soon come into mainstream in coming future. So like another advantage is the similar to that, we can see that wall panels can be very effective compared to a normal masonry work. So this is what we are doing at Earth. So there is a lot of possibility of extending these concepts to space applications as well. So people have demonstrated at very I would say primitive stages so far. So why is construction in space needed at all? So this could be for landing pads, roads, structural foundations. So these are type of 2D construction, and we go talk about the habitats, garage, radiation shelters. So those would come into like 3D construction segments, and also for some infrastructure needs for the planetary space missions. And why these missions are there? So definitely at the end, there is a business need and there is a scientific curiosity behind these explorations. So you must be knowing that there are a lot of rare earth minerals which are there, which are found to be there in the asteroids on Moon and Mars. So definitely mining has become a good kind of a business. There have been like more than, I would say, 50 startups in US who are actually just looking it as a business opportunity for mining Moon. Like Moon Express is there. Even alumni of IIT Roorkee, Mr. Naveen Jain has found a company, Moon Mining, a Moon Express, for this thing. Also, another interesting thing in space is the microgravity environment. So a lot of new manufacturing concepts can come in space. So people are trying to do bioprinting because their gravity is not there. So then you can actually deposit layers very effectively without fearing that that would settle down. So those microgravity environment are actually exploring new avenues of manufacturing like bioprinting. Also, there is a company in US, Silicon Valley based. They are introducing like Z-Bland. This is a new material which can replace the existing fibers which are used for communication, and that have a transmission capacity which is like 5 times better when those are produced in microgravity. So, and that microgravity manufacturing actually reduces the I would say the challenges or limitations in the manufacturing process. So the errors reduce. So these kind of things are also putting a emphasis on having habitats on Moon and Mars. And space tourism and space exploration always has been a key driver for having a habitat in Moon, Mars, or space. So what challenges do we face? So even construction on Earth is not that simple. So how would that become possible in space or Mars or Moon? So first of all, if we look into the construction in Martian or lunar environment, we have to understand the nature of soil that is present there. What kind of minerals can we extract from that soil? What kind of binding agent would be there? Because on Earth we use cement to bind, but what would happen? And for effectively using cement, we need water. But how would we use the binding agents on lunar or Martian environment where we do not have any any kind of environment? So there is no pressure around us, and because of that, micrometeoroids can be there, and because of very low gravity, so how would the deposition be there? How would the interactions be there? And how would the material actually how all those reactions would take place if we are using basalt extracted from lunar regolith or Martian regolith? So all those things have to be understood. And how the actual the even if let's say we print a structure, so what would be the effect of that harsh environment? in long terms. So durability again would be a question. So if you want to develop habitats on these things, so there have been some possible ways which have been proposed, like to bring fully functional habitation modules. I think in coming talks we would be discussing about this thing as well, like the modules which can be inflated and then used on space explorations, or we can like dig some surface, like we can create some cave and then again use those habitation module in those caves, so that that cave could provide a radiation shielding. So that could also be done. Or we could use in situ resource utilization, ISRU, by using that local soil, local regolith, then processing it a bit, extracting certain material which can be used for printing, and then machines can be deployed which print the structure like layer by layer. So what first of all is required in undertaking this task is we have to simulate the regolith or the soil at Mars or Moon. So we have to understand what is the behavior of that soil in terms of shape, size, and its chemical composition as well. And then at the end, we have to demonstrate that it is economical as well at scale when we are trying to develop that structure. So people have tried to simulate and print the lunar and Martian regoliths, which have been at disposal to various agencies like NASA as well. So you can see the shape of lunar regolith is different compared to a Martian regolith, and that would be specific to a certain special geometry, special location as well. So this can actually change, like on Earth, you can say the soil condition changes a lot depending on the like location. So somewhere we have like this black soil, somewhere we have different soil, and all the soils have different properties. So that also would be a case there. And people have tried to demonstrate that these kind of simulants can be printed, but the results have not been very satisfactory so far. Like the output of this has been very a product which is having very low Young's modulus, which is not capable to actually sustain the load of itself, keep aside the load of other things. And all these studies have been done in like ambient condition, where we have not created vacuum, where there is like gravity of 9.8 g. So all those conditions are, so the state of the art, I would say, is still lacking very behind from the actual conditions that we would have in space. So what considerations do we need to have is, there can be a way like either we just create a controlled environment, like where we pressurize the entire environment, although the gravity would be different, but we can control the pressure, and then in that inflated environment we can do the printing using robots, or we develop printers in a way that can actually print on that environment of Moon or Mars. So there could be a monolithic construction, or there could be a modular construction. I'll show a video later as well, where both of these kind of things would be explained, like in concept primarily. And what would be the design considerations? So we know that there have been moonquakes, but those are not as strong as Earth, and gravity is definitely different compared to Earth. So these two loads are lesser compared to Earth. However, the thermoelastic loads are very high, because the temperature variation is very high on both Moon and Mars, because there is no environment to actually provide a blanket effect. So that is a very major concern for like developing habitats, because shrinkage and expansion that would lead to thermal cracking. So that has to be considered. Then another thing would be the pressure, because of the like environment on Moon and Mars. So we have to ensure that there is a pressurized chamber where people can live in. So we can do two things: either we have just a shell, and in that shell we have a pressurized chamber module, or which can touch or which can take support from the outer shell, or which cannot. So if we actually get the inside module in touch with the outer shell, then that would put pressure on the shell. So we have to design that structure accordingly, or we can actually leave the gap between the inner module. Yeah, or we can have a separate inner module from the outer printed shell, which can just act as kind of a radiation shield. And then also the normal loads, it could be a self-sufficient structure, which would restrict all the micrometeoroids, all the radiation shielding, and then inside we could have an inflatable module. So basically we have to ensure that there is no penetration of micrometeoroids, and radiations are restricted inside that printed chamber. And to do that, people have demonstrated that 1 to 2 meter thick layer of regolith could be sufficient. So that can be actually done using a 3D printed procedure or manufacturing process. So in line with this, NASA started a challenge for building Martian homes, and they started in like 2016. That was a 3-stage challenge where they were looking for a in situ resource utilization, basically ISRU, and they wanted that a concept which can work on like Martian environment, then how you would develop using the in situ material ISRU concept. And then they wanted the teams to fabricate and then show that these can be printed to a certain subscale level. So
Marcia
see,
is our
AI
proposal
SpaceX.
for a Martian surface habitat.
Look at this video.
It's born of a careful response to the Martian environment and a synergy between structural, architectural, and construction principles with human experience at the center. The first task for any Martian home is to hold an Earth-like atmosphere. A simple trade study of spatial and material efficiency shows that a vertically oriented cylinder is the best formal basis for a surface habitat. Apart from being highly effective pressure vessels, they provide the greatest ratios of usable floor area to surface area and usable floor area to volume and diameter. Reducing surface area means using less material under less stress. Reducing volume means reducing energy loads on mechanical systems. And reducing diameter directly reduces structural stresses, especially at the base where uplift forces will require anchorage into uncertain ground. Unlike domes, they do not produce unusable overhead volume or unusable perimeter floor area. Therefore, the most direct way to reduce structural loading and maximize usable space is to reduce the diameter and add space vertically. This configuration also lends itself exceptionally well to joining and separating mission activities in a meaningful way by level, avoiding the need to divide one large area into lots of small, confined spaces. Finally, vertical cylinders are also inherently the most printable pressure vessel, and their resulting smaller footprint aids in construction by reducing the printer's required range of mobility. Apart from pressurization, Mars's drastic thermal swings means that any structure not allowed to expand and contract will fail. Our solution to this is twofold. At the ground, we render the shell and its base as a single structure, a flanged shell that moves on sliding bearings at its contact with the ground,
So this is the
while
base
clamps
isolation
and
concept,
soil
which is
anchors
also used.
secure the flange against uplift. And inside, we separated the pressure vessel from the habitable area entirely, resulting in a double shell system with many architectural uses. Since it does not hold an atmosphere, the inner shell is
So this is kind of a complete
Welcome to the
structure.
Mars Incubator. This habitat is created from in situ material.
So that was a complete monolithic structure. So now there is another concept where like this could be a modular concept.
For efficient construction and provides a safe and robust environment for human life on Mars. It consists of 4 distinguished volumes separated into functional zones. The first volume is a vestibule for surface deployment via suits and rovers. The second and primary volume contains lab space, ECLS systems, a sanitation facility, a food prep area, and accommodations for crew members. The third volume is a flexible space for multiple activities, and the fourth volume is the biogeneration area designated for plant growth. All of these are connected with adjustable bridges that are welded into place. Before any volumes are placed, the external support structures are formed by adding successive layers of laser-melted basalt fiber in a fused deposition. Next, the lower panels of the habitat exterior are placed on the external supports. These panels are made from regolith and polyethylene and are reinforced with impact-resistant fibers. The properties of these materials allow for effective pressure retention and protection from impacts and radiation. This process allows for multiple configurations of the panels to be manufactured with the same process and equipment. With the lower panels in place, the internal components can be assembled on top. These parts are comprised of long fiber reinforced polyethylene.
So like similarly, another few concepts have been there. So people are demonstrating multiple like episcore. So there have been a lot of new concepts in place where people have demonstrated that how we can actually uh, do a Martian mission where we can do the habitation on Moon and Mars. So still we need to study the effects of 3D printing in like extraterrestrial environment. We need to study the behavior and suitability of extraterrestrial soil for this mission. Like also we need to develop simulants, regolith simulants, which we can do print here. And we then have to develop like vacuum conditions where we can just develop these structures and then understand the behavior of those printed structure in those environments. And then we have to also adapt our existing manufacturing or printing capabilities. The machinery has to change to account for the like smaller gravity and also like exposure to harsh environment as well. And then the we have to understand what is the durability, what is the strength, what are all the parameters which are required for a regular construction, and how those actually would behave in the long term. So what we need is like ISRO could heed towards ISRO, which is in situ resource utilization. Thank you. We can go for questions if any.
Yeah. Thank you, Shashank, for such a wonderful talk. I'm sure all participants must have enjoyed going from Earth to Mars and Moon, and with the help of 3D printing. So now we have the question and answer session. So participants can directly unmute themselves and ask questions to Mr. Shashank.
Hello. Hello. Can you hear me?
Yeah, go ahead.
I have a question. Thanks for the good talk. I was just wondering, all these 3D printed structures, how do you make them permanent? How do you anchor them permanently onto the ground? Like you print it off-site, and like there's a construction going on next to my building, and they spent many months creating a piece. So how does one go about this?
Okay, so I'll just show you how it can be done. So basically we can provide anchors. There can be vertical anchors. Let me show you if I can see. So this could be done through bolting or anchoring. Let me see. Yeah.
You need basically
you can
foundation
look at this.
boards.
Yeah.
Is it,
So this
Shashank?
kind of, sorry, sir?
You need foundation boards to be embedded.
Yeah, kind of. So we can actually have like something which is coming out from foundation board and which would go into the superstructure. So, or you can actually like embed some like anchoring, vertical anchoring from top, hammer it down like the pile foundation is done. So similar to a pile foundation that can be hammered into the ground. So once that is hammered and fixed to the ground, then that can be a good stable structure.
Okay. Thank you.
Hello.
Yeah, hello.
Yes, sir. I have a question. So, can the resulting object that we are making, can they be recycled back into the original material for reprinting?
In that case, I would say that is possible, but that is an energy intensive process again. Once we have the concrete which is hardened in state, so then you have to crush it, so to reuse it. And for crushing, you need to have like crushing plants, pelletizing plants, which would like either make it into a particle size of 4 mm or 4 to 18 mm, which can be used for regular construction. If you want to use it in 3D concrete printing, then that has to be like made into a powder form, which is below 4 mm in particle size. Because so far, no concrete printing application has been demonstrated which could use like 12 mm regular aggregates. So yes, that material can be used, and that can be used as a replacement of sand by crushing the concrete.
Okay, sir. So are the plants set up in India?
Yeah, there are crushing plants, there are pelletizers available. So you can send the debris to those plants. Those plants are located like even in, I would say, Ahmedabad also are some one or two plants are there. And then you can get back the material. But that is an energy intensive process. Yes.
Okay, sir. Thank you.
Okay, Shashank, I have a question. So you mentioned about setting up habitats on Moon and Mars, and as we know that for Moon there is no atmosphere. So is it just a thickness dependent? The thickness aspect which will prevent the space radiation because these are high energy particles coming from space, or you even plan actually mix with certain kind of material, of course making use of the locally available minerals, which will prevent it in much more efficient way. And my second question is, before going to Moon and Mars, what is the future of affordable housing through such 3D printing in India? For a country like India, we need affordable housing. So what are the future prospects?
So Chintamani, so like first question, so far there have been research which shows that there is a one method of thickening the walls which could be a effective radiation shielding. So like they have demonstrated that 1 meter should be sufficient for radiation shielding for certain cases. So still a lot more research is required for different like locations. Like the location would also be a key factor, like where the radiation would change. And also material needs to be studied. So there people are researching on this aspect. So I'm not much into that radiation shielding study, but yeah, people are searching on that aspect as well. Now coming to your point on like how like valid or feasible this technology could be for Mars housing, so I would say yes, this is feasible technology. We have demonstrated some. So I would say like we have got orders from Indian Army which would be replacing the conventional bunkers, so which are priced at somewhere around 4.5 to 5 lakhs, and we are going to supply those bunkers at a same price, and that would actually be built like in a day or two only, compared to like 20 days or 25 days, and those are blast resistant, impact resistant. So the technology has certain advantages as compared to conventional, and this is getting like into the mainstream. And I would say to commit to Mars housing, it would still need some time because you have to have certain permits and all. But with Army there is an advantage that they are ready to take that new technology, and then we that can be very fast. So once those things get absorbed in like in defense, then it would be easier for it to percolate into the regular system for building construction. Yes, and this is feasible. People have demonstrated it, and yes, it should be in mainstream in few years from today.
Thank you so much.
Anyone else?
Any questions from YouTube? Hari, can you just check?
1 second.
Okay, Shashank, I want to ask one thing. Of course, you have shown also when we go to the moon, the gravity is 1/6
Yes, sir.
G/6. Okay, and the whatever machines we make for Earth, they are working under gravity. So how to take care of those things at the moon? That is the first thing. You will have to do some experiment or make a setup at the Earth, where you make the gravity G/6 and test your system. Then only we'll go to the moon and finally do it there. So we can't go directly at the moon and make a trial. So for the trial purpose, we'll have to develop some system. So definitely it needs some amount of R&D, how to test all those systems at 1/6 of the gravity. So is there any effort going on in this field, either in India or abroad?
So, sir, if we look at the International Space Station, so all the work done at International Space Station is at microgravity, and they have robotic setups. So all those robotic setups are similar to that, can be extended to like Martian or lunar environment as well, because we are like working at a close to zero gravity. And if we have robotic solution for that environment, definitely there is a midway where we can go for 1/6 of gravity. And those are so readily available. There have been companies which have demonstrated that like there can be robotic solutions to this kind of environment as well.
It means whatever people are using in International Space Station, that can be utilized at the ground for testing all those systems.
Kind of, sir. Yes.
Kind of. So it
Because-
means there is a good amount of scope available for our young engineers as well as academicians, those who are in the field of teaching. Then they can take up these type of exercise. You know how to develop a system to for 3D printing where the gravity is g by 6. So we don't know what they are doing actually in the space shuttle kind of thing. But if you know, when they train the astronauts, you know, for astronauts training, they give everything at the ground only. So they have made very good system in Russia and America for testing of astronauts. And India also has sent their 4 astronauts for Gaganyaan project to Russia, Moscow. They have made a very old center in Russia where astronauts from other countries also come for the training there. So these facilities are not so easy to make. It involves a lot of cost, time, place, policy, everything. And other than that, there is a good amount of scope for the young engineer, those who are attending this program, those who want to do some business with some research mind. Okay. There is for normal business, of course, there are so many items are available in the market. So if you want to do something good for the country or you want to do related based on science. So this is a field, what Shashank is doing. Now at the moon, we'll have to make so many houses. Later on, what to do, whatever research we'll have to do. So using 3D printing, we can go there. You must have read in the newspaper also that L&T, Bombay, they have also made one house using 3D printing.
Yeah.
Okay, that news was there. So like L&T is coming, they want to make, do the large construction, means mass construction for these very economical houses, which government wants, 1 room kitchen set for the per people. So they want to use these particular techniques. So there is a good amount of scope available for our all young boys who are here attending this, but they can work in this particular field. And I think Shashank also is doing, which is not mentioned, he's also running a company in Ahmedabad. He has established his own startup where he's making a lot of furniture items like, you know, chairs, tables and other things using 3D printing. So I think time is there. If Shashank is ready and he has got a PPT for that, I think it can be shown. Shashank, do you have something on that?
Okay, sir.
The activities of your company, Maiko?
Yes, I can show.
So you can replace the wooden furniture, steel furniture. You know, you must have seen a lot of people are making cast iron furniture, MS furniture, which gets rusted very fast in open areas. And if you make in wood, wood is also becoming very costly. So people have started making in glass fiber this furniture. Glass fiber again is a prone to ultraviolet rays. The life is very less. When you keep it outside, it will break, it will become brittle. So there is one solution for this is 3D printing. And ISRO is also making one center, I think somewhere in Karnataka, Chitradurga, where they want to simulate the surface of moon.
Okay.
Okay. Like our lander and rover, we want to land on the moon. So we are just simulating. So a special type of soils they have developed, one company has developed, which is matching with the soil at moon. Okay, you can be in touch with them and get some sample who is that company making this kind of soil. You can do it.
Yes, sir.
And there was another news I read somewhere in that Dubai, Dubai, they are making a big Martian city, the total concept of the Mars. Now they are making in Dubai that shelter and everything. So if you enter inside that, you will feel that you are on the Mars. So all the environment, everything, even the soil, they are making compatible with Mars. So those who are interested in this type of research, they can just find more and more details on that. So after Shashank makes a presentation on his company, then we will invite after that Pankaj Kumar for his presentation. Yeah, Shashank, could you get something?
Fine, sir. So I'll
No.
just sir, show few images.
Few
that we have-
photographs, either images or something, you can show it.
Yeah, sure, sir. Okay.
And you see bottom there is one photograph furniture
Yes, sir.
at this.
The, So, sir, this one is placed at ISRO.
Hmm.
Yeah.
At our ISRO colony, Vikram Nagar. So one this type of chair he gifted to us, so which we have kept there.
So this
And-
was our first print. So we
Hmm.
tried to print a pie, like a unique shape, and then all these were like printed in just a matter of 15 minutes. So if you
Hmm.
look at the prototyping time has reduced a lot. So in 10 to 15 minutes, we could print a single article, and then like there could be polishing, finishing, a lot of things. So we have like populated IIT Gandhinagar campus so far with our furniture, and so people are liking it as well. A lot of query has been there to us for supplying these, but due to COVID, in past through 2-3 months, we were not able to actually do much. Also, like we have been setting up a very larger factory. So this is our new production area, which is on SG highway, and it should be running in by June end, where we plan to actually develop all our furniture. So we would be setting up a very large scale factory, large scale gantry system. At least 2 such gantry, large scale gantry would be there for development of the furniture and wall panels, bunkers and all. So you would be welcome to actually visit this facility. It's on SG Highway, India Container Corporation of India. Would be amongst the world's biggest 3D printing facilities. So anytime anybody can come and then experience 3D printing at large scale. Yes, sir.
In fact, ISRO team wanted to visit IIT Gandhinagar and see your facilities, but because of this all COVID problem and other commitments, they
Now,
could
sir,
not
we have
do that.
moved from IIT Gandhinagar. We have
Ah.
removed our setup from IIT Gandhinagar.
So they will come and see this Concours Center is also not very far from.
Yes, sir.
It
Nearby.
is half the distance,
Actually, sir.
very near to also. So they can come anytime to that place.
Yes, sir.
And
Yes, capacity building team can visit them.
yeah.
Okay.
So ISRO, that
very
civil
good.
engineering team, they
Yeah.
not only they wanted to buy some furniture from you
Okay.
for our colony, etc. They wanted to make some of the special items which can be used in the campus
Okay.
using 3D printing process. So let us wait for some more time.
Yeah, sir.
Maybe.
Times are tough right now, sir.
Yeah. Okay. Thank you, Shashank. Thank you very much for sparing your time and agreeing on our request to make a presentation here. And I hope your presentation and the concept what we have been would be very useful for the young engineers, those who are attending the program here.
So thank you, sir. It's always been a pleasure.
Thank you. All the best
Thank you.
for your company. Thank you. Okay, we welcome Mr. Pankaj Kumar now.
Hello.
Pankaj, you are there?
Yes, sir.
Yeah,
Hello.
good. In fact, Pankaj is a young engineer who came in my contact in 2019 when we organized a national level seminar with Dr. Sanjeev Upadhyay of IIT Roorkee. That seminar was on inflatable structures and it was not online, it was in physical form. And that time around 90 engineers from all over the country, they came and attended that particular event. And that time the Pankaj was there, he came from Bhopal, but now he is in Noida. And if I remember correctly, he came from the Bangalore, asked so many questions related with inflatable technology. He has shown a lot of interest in space related jobs. And that time he said, no, right now I am involved in making dishwashers. Is it correct?
Yes, sir.
Yeah. So he was into that thing. So later on also he has shown a lot of interest in most of our awareness programs he is attending. And this time also he said, no sir, I have got a lot of interest in 3D printing as well as in space. So I said, okay, you can work in this particular area. when our astronauts go to space or they go and settle down at the moon, they'll have to stay for a longer period. Like now, International Space Shuttle astronauts go and stay there for 6 months together. So that way, many countries are planning to take their astronauts and they will be staying at moon. So, what type of houses will be there at moon? So a lot of people are working, the civil engineers, architect, the mining people. Okay. And in fact, I have made a WhatsApp group also. There are around 45 young boys there, those who have interest into this. And they are asking, sir, let us have some activity on this moon habitats. Okay. Anyway, idea is not bad. It is a good idea. We'll have definitely some time in full day activity on moon habitats. So that way, this interest was created in Pankaj Kumar, and recently he said, "I made some presentation. I could think of about some ideas how to generate power in the because." What Shashank has explained, that 3D printing machine, we need power also. From where that power will come? The power will come, I think, mostly from the solar energy. So we
Yes,
will have
sir.
to use solar panels and other things. Then we need oxygen to breathe there. So from where we'll get oxygen, and what are the other materials which can be used? So anyway, he prepared one presentation on that. Definitely, we should encourage such young people. Once they get good ideas, let them present in these type of forums. So that way only I think the country will progress, and they will be very useful in ISRO in future. So now, Pankaj, I request you with this introduction about you to make a presentation.
Yes, sir. Hello. Good afternoon, everyone. Sir, आवाज आ रही है?
हाँ, आवाज आ रही है, बहुत क्लियर आवाज है आपकी. हाँ.
My name is Pankaj Kumar. I am BE Mechanical Engineer from Bhopal. Now I am job at 3D Fusion, Sector 10, Noida. अब मैं मून के ऊपर घर कैसे बनाएंगे उसके बारे में पीपीटी प्रेजेंट कर रहा हूँ. हेलो.
Are you trying to load your presentation?
सर मेरी प्रेजेंटेशन इसमें शो नहीं हो रही है.
फिर से जरा एक बार ट्राई करो. Chintamani, can you allow him to load his presentation?
Yes, sir. I have already given,
Permission to him.
Yes.
Okay. You are having a laptop, no?
Yes, sir.
So you try again. I think it will come. You go to the share screen.
Yes, sir.
Then some windows will come. You click at the center of that.
Yes, sir.
Okay.
Okay, sir.
Okay. Now you can open your file, that PPT file in your computer. You can what you call it. थोड़ा इसको minimize कर दो और अपनी फाइल खोलो.
ठीक है सर, कर रहा हूँ.
अपनी फाइल खोल दो उसमें कंप्यूटर में पहले.
Pankaj, just let us know if you're facing any issues.
नहीं, सब ठीक है। Yes.
Okay, Pankaj, may I know what problem you are facing?
सर इसमें साइन इन कर रहा हूँ तो ये सिस्टम ऑफ हो जा रही है।
Hmm,
ये दूसरा कुछ ट्राई कर।
okay, maybe what you can do, try rejoining from your desktop, and then you can share the screen.
ओके। सर फोन से भी शेयर हो सकता है?
No, if
Hello?
your presentation is on phone, then only it can be shared.
हाँ, प्रेजेंटेशन फोन में भी है।
So if presentation is on phone, then it is possible. Otherwise, but I will suggest that better you can share it from your desktop, because you'll have a better control.
ओके। इसमें तो
So right now you have logged in from mobile or desktop.
बहुत दोनों से।
Okay. Okay, do one thing. First, only join from the desktop first, and you can share the screen. Let us try that.
ओके। Is it visible?
See, but what I can see is you are trying to do it from your mobile, right? Your
Actually,
mobile is being focused on your laptop, right?
yes.
Yeah. So instead of that, I will prefer that you log in from laptop, and then share your screen, because this way it may not be good, for viewers.
इससे डेस्कटॉप से सब
So can you just show if you have also logged in from desktop? Can
yes.
you just show the Zoom window on desktop? Can you open the Zoom link from desktop?
Yes, sir. Yeah.
If you do not have Zoom installed, you can open it online also.
ये प्रॉब्लम
Okay, or what you can do otherwise, if you can share your presentation via WhatsApp to Mathur sir, or we can then run it and you can speak.
Yes, yes, yes. मैं शेयर करता हूँ.
If you can send it by email or WhatsApp.
व्हाट्सएप पे माथुर सर को शेयर करता हूँ.
I have your old presentation. Should I show that?
Yes, sir.
There may not be much. There may not be much changes.
सर मैं इसमें थोड़ा सा चेंजेस किया था.
ठीक है. थोड़ा बहुत तो चलेगा. Otherwise, you'll have to send me fresh.
Pankaj, I request if you can send your presentation to Mathur sir right away.
Can you send from your computer by email?
Yes, sir. आप ही शेयर कर दीजिए. सर वही पुराना वाला शेयर कर दीजिए.
पुराना वाला शेयर कर देता हूँ. चलिए.
Yes, sir.
I'll try that. आपको मुझे परमिशन देनी पड़ेगी चिंतामणि जी.
Sir, you already have permission.
Okay.
We can see your screen.
You can see my screen.
Yes.
Okay. Then.
Sir, you'll have to just start the slideshow.
Okay. Is it okay?
Yes, yes, sir.
Okay, Pankaj. I'll
Yes,
put
sir.
your first slide. This was the first slide with me.
Yes, sir.
Now you can speak from your system.
पावर पॉइंट प्रेजेंटेशन ऑन मून, मतलब मून के हमें लॉन्ग टर्म में जाके रहने के लिए 6 महीना 1 साल हम कैसे रहेंगे उसके बारे में पावर पॉइंट प्रेजेंटेशन बनाया है.
आप हिंदी में भी बोल सकते हैं. हिंदी इंग्लिश कोई भी लैंग्वेज में.
यस सर, हिंदी में बोल रहा हूँ. नेक्स्ट सर.
चलिए नेक्स्ट चेंज करूं.
यस सर. Facts about moon. The moon is Earth's only natural satellite and the largest moon is the solar system. The moon presence helps stabilize our planet, over which helps stabilize our climate. The moon is distance Earth is about 24000 miles and 38400 km. The moon has a very thin atmosphere called an exosphere. The moon's entire surface is created and weighted from impacts. Next, sir. Some images of moon. मतलब हमें मून कैसे दिखता है इसमें फोटोज दिया है. फर्स्ट, सेकंड, थर्ड, फोर्थ.
इसमें इमेज में कुछ एक्सप्लेन करना चाहोगे? कौन को 3-4 इमेज दिखाई है आपने?
सर इसमें
मून की सरफेस पे दिखाए काफी गड्ढे बने हुए हैं.
यस सर. इसमें गड्ढे में जो मतलब मून के ऊपर एटमॉस्फेयर नहीं है, इससे हवा नहीं बनती है, इसलिए मून का सरफेस जैसा रहता है वैसे ही दिख रहा है. साइज और डिस्टेंस. इसमें कुछ इमेजेस शेयर की है. The Earth, Moon and Sun with a radius about 174 kilometer. Moon का जो radius है 174 kilometer है. The Moon is less than a third of the width of Earth. That means 30 Earth-sized planets would fit in between Earth and Moon. The Moon is slowly moving away from Earth, getting about each other. मतलब हर साल 1 इंच मून हमारे पृथ्वी से बढ़ते जाता है.
नेक्स्ट.
Yes, sir. The moon.
इसमें क्या फॉर्मेट की वजह से थोड़ा सेटिंग डिस्टर्ब हो गई होगी?
सर एक मिनट में आपको खोल दूंगा।
खाली टाइटल थोड़ा डिस्टर्ब हुआ है, बाकी तो आ रहा है। दिखाई दे रहा है ना पंकज आपको?
यस सर, यस सर, बस मैं खोल दूंगा। साइज एंड डिस्टेंस इसमें तो हो गया सर। नेक्स्ट, हाँ सर, orbit or rotation. The moon makes a complete orbit around Earth in 27 Earth days and rotates or spins at the same rate or in that same amount of time. Because Earth is moving as well, rotating on its axis as it orbits the sun. From our perspective, the moon appears or orbit in 29 days.
नेक्स्ट,
फॉर्मेशन ऑफ मून। नहीं सर, अभी से बोलना। फॉर्मेशन, द लीडिंग थ्योरी ऑफ द मून्स origin is that a Mars-sized body is collided with Earth about 4.5 billion years ago. The resulting debris from both Earth and the impactor accumulated from our natural satellite 239,000 miles, 384,000 kilometers away. The newly found moon was a molten state, but within about 100 million years, most of the global magma, ocean, and crystallized with less dense rocks floating upward and eventually forming the lunar crust. इसके images में मून का फॉर्मेशन दिखाया है, कैसे बना हुआ है। ये हमारा जो लेफ्ट बॉटम लेफ्ट राइट नीचे प्रोग्राम है, ये फाइनल मून है। नेक्स्ट सर,
नेक्स्ट चेंज नहीं हो रही है। चलिए,
surface the temperature of the moon reaches about 172 degrees Celsius when full sun, but in darkness the temperature plummets to about 173 Celsius. In this picture we show, so दिखाया गया इसका टेम्परेचर 170 डिग्री से माइनस टू 178 डिग्री सेल्सियस तक जाता है।
नेक्स्ट,
Yes, sir. Water on the moon. During the initial exploration of the moon and the analysis of the return samples from the Apollo and the lunar missions, we found that the surface of the moon was dry. Water on the moon is in some places as ice. कुछ समय पहले मून पे पानी पाया गया था, लेकिन अभी बर्फ के फॉर्म में मिलता है। इस इमेजेस में दिखाया गया है। नेक्स्ट सर, जब हम मून पे लॉन्ग टर्म के लिए जाएंगे तो हमें किन किन चीजों की जरूरत होगी, जैसे हमें सब रहना होगा, तो what things that I need to live on the moon? Oxygen, house, electricity, food, suits, research on the moon. और हम वहाँ पे जाकर जो रिसर्च करेंगे, मून की सरफेस कैसे है, एनवायरनमेंट कैसा है, हमारे लिए क्या स्कूल है, SRHs. Next slide. The process of making oxygen or hydrogen on the moon. We will how to making oxygen on the moon. We will convert ice on the moon into the water. We will separate hydrogen and oxygen from water. We will use oxygen to breathe. We will use hydrogen as a coal. मतलब हमारे पास जो ऑक्सीजन मिलेगा हम उससे सांस लेने के लिए यूज करेंगे और वहाँ पे एटमॉस्फेयर बनाने के लिए भी उसका यूज कर सकते हैं। और जो हाइड्रोजन ऑक्सीजन को सेपरेट करेंगे उसमें हमें हाइड्रोजन जो मिलेगा हम उसको एज ए फ्यूल भी यूज कर सकते हैं। नेक्स्ट
नेक्स्ट चेंज नहीं हो रही स्लाइड, बीच में हैंग हो जाता है।
the process of building a house of the moon. We will use the soil of the moon to build house on moon. Whose temperature capacity will be from 260 to 260 Fahrenheit to minus 280 Fahrenheit. We will use 3D printing technology to build house. To build the house, we will take the entire setup of 3D printer from the Earth to the moon, and we'll start this machine by assembling there. We will use AC to maintain temperature of the room. No. कुछ दिनों पहले अभी IIT मद्रास में 3D printing के हेल्प से एक घर बनाया गया है और हम उसी टेक्नोलॉजी का वहाँ पर भी यूज करके घर बना सकते हैं। उस टेक्नोलॉजी में टवस्टा थी। तो टवस्टा is a startup alumni of IIT Madras constructed India's first 3D printed house. The startup devised concrete 3D printing technology to single a story house with functional space of about 600 square feet. और comparing a single bedroom hall और kitchen, इसमें एक पूरी complete 3D printing से घर बनाई गई है। Intertable material, we will use the material to build house. Intertable material से हम घर भी बनाने की कोशिश करेंगे। ये बहुत ही मजबूत फ्लेक्सिबल मटेरियल होता है जिसको हम जैसे चाहे वैसे स्टोर भी कर सकते हैं और इजी टू कहीं भी लेकर जा सकते हैं। This material is very strong and flexible. We can make it be worn by using it. हम जैसा चाहे इसे वैसा बना सकते हैं। To build a house with 3D printer, we will use the clay of the moon. With a 3D printer, we will build a house according to our requirement. हम अपने जरूरत के अनुसार वहाँ पे 3D print से घर बना सकते हैं जिनको हम अपनी मिट्टी को यूज करते हैं। There will be a water tank in the house that we will store the ice by melting it. The design of the house will be such that we take oxygen well. The house will be in the washroom that is daily. We will take some things from the earth to exercise. जो लोग स्पेस में जाते हैं उनको एक्सरसाइज करने की भी जरूरत होती है। वहाँ पर डेली एक्सरसाइज करना पड़ता है। Next, how to generate electricity on the moon. The optimum solution is using huge mirror like solar reflectors installed on satellite in orbit, which will which will concrete energy from the concentrate energy from the sun onto solar panels. This in turn the energy into electromagnetic radiation, which is beamed back to Earth, either laser or microwave from my antenna. हम लोग वहाँ पे इलेक्ट्रिसिटी के लिए सोलर का यूज करेंगे. We will use solar energy to use electricity on the moon. We will use hydrogen fuel for backup. हम वहाँ पे backup के लिए hydrogen fuel का यूज करेंगे. We will use solar energy for solar energy को heavily use करेंगे. We will also use solar energy for research work. हम लोग वहाँ पे जब जाएंगे तो कुछ research करेंगे, उसमें solar energy का use करेंगे. Fourth, we will use greenhouse technology to grow plants and vegetables. Greenhouse technology ऐसी टेक्नोलॉजी है कि हम किसी भी environment में अपने according जैसा चाहे वैसा फल और सब्जी हम अनाज उगा सकते हैं, जैसा कि हम डेली यूज करते हैं. Greenhouse technology is the technique of providing favorable environment conditions to the planet. It is rather used to protect the planet from the adverse climatic conditions such as wind, cold, reception, accession, radiation, extreme temperature, insect and diseases. किसी भी कंडीशन में हमें इसमें फल सब्जी उगाने की सुविधा होती है. Space search for astronauts. We will prepare a special search for astronauts, which will use a house. We will use other types of suits outside the house. हमारे स्टूडेंट्स के लिए जो घर में रहेंगे उसके लिए स्पेशल सूट होगा, और घर से वहां जब रिसर्च करने के लिए जाएंगे तो उनके लिए भी कुछ स्पेशल सूट्स होंगे. Listen to the moon. We will make a launch station on the moon. Rocket will not have to be made very strong by launching from air, because we value of pressure forces 1/6. हमारा मिशन यह है कि हम चंद्रमा पे जाके जो एक स्पेस लॉन्चिंग स्टेशन बनाएंगे, जिससे कि हमें ज्यादा स्ट्रॉन्ग नहीं बनाना पड़ेगा. धरती पर से लॉन्च करने के लिए हमें ग्रेविटेशनल फोर्स को लॉस करना पड़ता है. इसके लिए हमें बहुत ही हेवी रॉकेट को बनाना पड़ता है, और वहाँ पे ग्रेविटी भी कम है. It is made very strong for sending rockets from the Earth because it has a cross to also gravity. Minerals. We will research the minerals in the soil of the moon. Our students will research on soil over there. What minerals are there in the soil? पौधे मिनरल्स के बारे में रिसर्च किया गया है कि इसमें क्या मूल जो मिट्टी है उसमें मिनरल्स क्या क्या है, और सॉइल में क्या क्या है, और हमें क्या मिनरल्स मिल सकता है. We will also research that minerals can be used to stay on moon for long time. We will also be proceeding some minerals as we do on Earth. We will establish factory on the moon to make minerals from alloy. हम वहाँ पे कुछ फैक्ट्री बनाएंगे और मिनरल्स की प्रोसेसिंग करके उसमें प्रोडक्ट भी बनाएंगे. उस प्रोडक्ट से पाएंगे है कि जो हम अर्थ पे प्रोसेस करते हैं और मून पे प्रोसेस करते हैं उनके प्रॉपर्टीज में काफी मिलती है, और वहाँ के कुछ जो मिनरल प्रोसेस होता है river. Some research has also revealed that there were earlier rivers on the world. What were the rivers like and how did they flow? What was found in these rivers? Did animals live in the waters of the rivers? What did the waters on the rivers into ice? हमारे जो रिसर्च होंगे उसमें ये जो पहले नदियां पाई जाती थी वो कैसी होती थी, रिवर्स कैसा दिखता था, उनकी पानी का फ्लो कैसा होता था और उस पानी में क्या क्या पाए जाते थे, कुछ एनिमल्स और जैसे पाए जाते हैं वैसे वहाँ पर पाए जाते थे, इसके बारे में हम वहाँ पर रिसर्च करेंगे. Moon light atlas, moon का कुछ atlas है तो इसमें दिखाया गया है टेलीस्कोप्स कैसा दिखता है, लूनार फॉर्मेशन कैसा है, लूनार Saturn day atlas. Yes sir.
I think that was the last slide. Okay. The presentation is over.
Yes sir.
So many
Yes,
slides
sir.
are there. I'll stop sharing.
Yes sir.
So Pankaj has interest and he made this presentation. Of course, he did some modification into that. The latest copy I was not having. So same way, many students, those who are attending this program, they may also have interest. They can work in all these particular technologies. And through their colleges, they can contact ISRO for more information related with that. Thank you, Pankaj. If anybody have any question with Pankaj, you can ask.
Sir, सभी को I am thankful to this company, Indian Space Industry Exhibitors, give me a chance to talk to all. Those who want to join me, I am sent the email. If any participant teachers wants to give me feedback on this, please mail me. So मैं share कर देता हूँ अपना email.
Okay. So I also have his email ID. If anybody needs, you can share it on the chat box. And I like to inform that ISRO sent our Chandrayaan-1 sometime in 2008. After that, lot of data we have received from Chandrayaan-1, even Chandrayaan-2 also. Lot of data is coming. We need more and more research scholars in the field of physics, at least, and geology, who can use that data for further research. We are lacking researchers. Data is there, a lot of data is there. And ISRO has made an atlas for Moon as well as on Mars. As we make atlas for the Earth, no, for a city, we mark all the places, give names to them. The same way ISRO has made a lunar science atlas. I will show you the cover. You will see that. And this is very thick. And you can see all the photographs.
Yes.
Okay. Same way, ISRO has made a atlas for Mars also. After launching our Mars mission. So the data about the Moon and Mars is available. Those who want to do research, they can write to ISRO, get these atlas, copy of those atlas, and use it. Okay, over to our Chintamani.
Okay, sir. So
our VK Jinsab is there today. No, I think he is also not joined.
so shall we move ahead with the next talk?
Yeah.
Okay. So our next talk is by
Dr. Sanjay Upadhyay.
So I welcome.
Yes, sir. Good afternoon.
Yeah, Sanjay, have you joined?
Yes, sir. Yes, sir. Good
Welcome,
afternoon.
Dr. Sanjay. Now we will have this talk. We have actually preponed. In place of Dr. Vishak Bhattacharya, we requested Sanjay Upadhyay to deliver his talk, and he is readily agreed. Not only this time, every time Dr. Sanjay agrees whenever we request him for a talk. So thank you very much, Dr. Sanjay, for spending your time.
Thank you, sir. Thank you.
So I think Chintamani, I'll give a brief intro of Dr. Sanjay.
Okay, sir.
Okay, you'll not be having. Yeah, I know Dr. Sanjay Upadhyay since long when he was in Gujarat before doing his PhD. He used to come to ISRO Ahmedabad for his research work. He has a lot of interest in working in the field of space science and technology. So that time on the smart materials, he was interested in inflatable structures and mechanism, everything. He did a lot of study in ISRO library. And after that, he was got under QIP program admission in IIT Roorkee. He did his PhD from IIT Roorkee. And finally, he was also absorbed there as a faculty member, associate professor. Now he is a professor in Mechanical and Industrial Engineering Department, IIT Roorkee. And he has a lot of interest related with the space science and technology project, working very closely with ISRO. And you know, IIT Roorkee has got a space technology cell in 2019. And under that, many projects have been given to IIT Roorkee. So he is very instrumental, Dr. Sanjay, in doing research, and already 3 projects I think he has completed with the fundings of ISRO on our smart antennas, inflatable antenna structure. Still now he's working on 2 or 3 different projects. I think he will tell you all of that. I did not tell. And just I'll tell you, Dr. Sanjay, he has got many patents to his credit. And at least around 75 or 80 research papers he has published in various journals of repute. More than 23 years experience he's got in the teaching of mechanical engineering subject in the vibration, mechanism, etc. And at least 9 PhD have been awarded under him. He has supervised 9 PhDs, 6 are already in progress, and more than 35 MTech students. They have done their dissertation under Dr. Sanjay Upadhyay, and more than I think BTech projects also. Many students are doing under him, and the list of sponsored research projects from ISRO and DRDO is very big. So I'm not going to read all that. So in fact, in brief, he is very active in interacting with ISRO as well as with DRDO and doing very fruitful projects. They are not all theoretical projects. You simply do that project and dump it. No, all these projects have got all practical utility, and ISRO is also appreciating all his work. And in ISRO Ahmedabad, he is very popular. People know he is a member of the Space Society of Mechanical Engineers. Other than that, at least 6 to 7 professional society he is attached. And he has visited a number of countries and related with these various paper presentation, attending conference, etc. And is a examiner, goes for his PhD vivas. He has come many times to Nirma University also. So now, without wasting much time, I'll invite Dr. Sanjay Upadhyay to speak on the inflatable space structure. So he has done a good amount of work, and those students or the faculty who are attending these programs, in case they have got some interest or they develop some interest in the field of inflatable structures for space, they can definitely contact Dr. Sanjay Upadhyay, and we can work jointly for the country. Thank you.
Thank you, sir. Thank you for nice introduction. So now I will share my screen here. Then after. So hope it's visible.
Yes.
Okay, sir. So good afternoon, all of you. As today I will give the topic on inflatable structures for space application. So just I want to brief the inflatable structure word I have received from the Mathur sir in 2005 when I was first time contacted him at SAC ISRO. At that time he was a group director. So since 2005 I attached with the Mathur sir, even ISRO other officials, and it's a long back journey from my the research with Mathur sir, and even every time when I approach the Mathur sir, every time he has supported me in any time on any part of activity. So today I will explain inflatable structures for space application, what we have done in IIT Roorkee. So before going to inflatable structures, just brief, I will introduce what is space application and what are the challenges in the space, why we are going for inflatable. So before, if you are going for inflatable, it is important to why we are going for inflatable because of some challenges in the space applications. So first, just I will show what is this. If I will ask you what is this, so there are lots of questions in our mind. Suppose this is a part of universe. Okay, so in part of universe, if you see and if you observe, now what you are visualizing in this. So if you see, so close your eye for a moment, and if you visualize, so imagine a clear sky in a night. So when you imagine, so have you felt a vastness of the universe? If yes, then definitely we will study of the universe, what is space, and why inflatable structures is required for the space. So let's start with the journey of the universe. There are number of things in the universe, galaxies, stars, everything where we are launching on our space shuttles. So now after observing this, if we see, so there are number of ideas are coming in our mind, number of questions arise in our mind. First one is, what is space? Obviously, if you study about the space, and if you want to launch the space shuttle in the space in orbit, so first of all in our mind, what is space? Hope all of you are aware about maybe, but we will get the answer. Second question is, our second thought in our minds, what are the challenges in the space? Suppose if you are aware about the space, then what are the challenges in the space? These are the second thought or the second question in our mind. What are the challenges in the space? Then why to explore the space? Why it is required? Okay, if you not explore the space, then what happened? So present whatever technology we are utilizing, we cannot utilize. So it is essential to explore the space. And how to explore the space? This is that's why our ISRO people, ISRO scientists, great scientists are working on this area. So how to explore the space? Then there are lots of ways to explore the space, but what is the optimum way to explore the space? Because when you launch the space shuttle in the orbit, so the thing will be counting on a per kg mass of sensor. So there are huge weight of the space shuttle, and when you launch in the orbit, so there are huge amount, huge energy, everything is involved in our economy. So optimum way to explore the space. So as a technocrat, as a technical person, we have to identify how to optimize how to optimize, so we can reduce our budget, we can reduce our energy, and more objectives, more gain, more objectives, more productivity we can achieve. So these are the questions in our mind. So first is, what is space and what is universe? Okay, so maybe you are aware what is space and what is universe. So what is universe? So in universe is everything we can touch, we can feel, we can sense, we can measure, we can detect, everything in the universe, including living things, planets, stars, galaxy, dust clouds, lights, everything is universe. And so what is in universe now? So contain of billions of galaxy, each contain billion of stars, time, space, all matters and energies. everything is in universe. So what is universe? What is in universe? Then is universe empty? No. The gas, hydrogen atoms, dust, and the other bits of matter float around the emptier of areas of the universe. While more crowded region can host planets, stars, and galaxies. So this is the definition of universe. And what are the available, what is in universe? Then what is the dimension of universe? Maybe we are not know exactly, but from the some literature we have received the age of universe, you see 13.799 plus or minus 0.221 billions of years. Then the diameter at least 91 billion of light years, mass, average density. So these are the dimensions of universe. This is available, we have received from the literature. So if you see the age, diameter, mass, average density, so all these things is in, this is the dimensions of universe. So now second question, what is space? Just why I am briefing you, because we are going on inflatable structures, and why inflatable structures is essential. That's why it is required to brief knowledge of this universe and space. So what is space? Space is zone that occurs about 100 kilometers above the planet. Is a vacuum, there is no sound, only wireless communication. Okay, so in space there is no sound, only wireless communication, and that's why we have sent these space shuttles in the orbit. So with the help of this, we can easily utilize, we can transmit any technology, or we can utilize this technology on Earth. So only radiations and conduction, heat transfer in vacuum. Okay, because there is a vacuum, there is no sound, so only wireless communication, and that's why we need to send the space shuttles in the orbit. Where no appreciable air to breathe, means too tough survival for living things, or scatter light, to drag difficult to control the motion, no frictional heating or high velocity. Is also filled with the radiations, magnetic fields, and high energy. So in this, this is the definitions of space. So now what are the challenges in the space? So there are lots of challenges in the space. So the space environment is a low Earth orbit, medium Earth orbit, and geosynchronized orbit, LEO, MEO, and GEO. So the low Earth orbit, medium Earth orbit, and geosynchronized orbit, geostationary orbit. If you see the temperature environment, thermal environment is around minus 190 degree to 160 degree. So thermal point of view, temperature point of view, you observe minus 190 to 160 degree. Then launch environment, acoustic field is very high intensity, 148 frequency range, this one. So there are lots of vibrations, temperature, everything we need as a technocrat, we need to study. So if you see here, the temperature, suppose when you launch when we launch the space shuttle in the orbit, okay, so sometimes directly exposed to the sun, and sometimes it's backside of the sun because it is completely rotation. Okay, so if we consider this is the sunlight or sun, so in position 1, if you see in eclipse, where is completely opposite to the sun, there is no light, sunlight. At that time, you are getting this is in full, in complete eclipse in position number 1. Then position number 2, if you see, so partially sunlight will be getting, and some is partially the dark point. So you are getting these types of the results where some temperatures were rising. So in final position number 5, if you see, this is a high temperature, directly exposed to the suns, directly contact to the suns. So all these challenges we need to identify, we need to rectify. the space environment is a natural environment and induced environment. Natural environment, exterior spacecraft and interior spacecraft. The exterior spacecraft, this is photon radiation, charge particle radiation, temperature effect, thermal thermal cycling. So these are the space environment. When we, as a technocrat, when we study any space point of view research, or when we do some research for a space oriented, so we need to consider all this part. Then thermal environment also. So onboard space hardware are subject to the significant temperature variations, because I already show you the eclipse and directly exposed to the sunlight. So the known thermal cycles, temperature variations depends on the orbit and spacecraft and hardware materials. So everything we need to consider when we are developing some space shuttles. You see temperature minus 190 to 160 degrees, exposure to the sun direct radiation, deep spacing, absence of convention in the space vacuum. Launch environment is also much more demanding combination of mechanical and thermal load, because when we launch, maybe if you are observing space shuttle when the launch, suppose in our Harikota, when we seen from the media or some news media, when space shuttle will launch, so there are lots of vibration, noise, heat, everything. So this is a combination of mechanical and thermal loads. So now how to explore the space? So by building the space structures, the space shuttles, PSLV, GSLV Mark III, it is our great scientists from ISRO. They have launched all this, successfully launched all these vehicles, launch vehicles. So if you compare this, their weight, height, so if you see the PSLV height is around 12-story building or scale 40 meters. GSLV Mark III, if you compare with their weight, so you see 245 times one ambassador or a Hindustan Motor ambassador's weight. Okay, the payload weight, you see payload weight is this. So lift of mass 320, 414, 640. So if you observe, when we are, the costing will be dependent on the each kilogram. So if you see, this is the weight is on tons. This is weight on tons. Okay, and day by day there are large space shuttles are required. Here if you are talking about the large space antenna, that means large reflector is required, because if you increase the size of the reflector, you can increase the size of the gain, and if you gain size is increased, so we can achieve more objectives. So these are the more challenging, how to reduce the weight, how to reduce the, much more important, how to reduce the weight. So these are the different space shuttles, spacecraft. Our ISRO people have successfully launched payload sensors. This is the means pictures of the space shuttle launch from their launching pad. So you see there are huge space is required, large volume, everything involved in large scale. So as a technocrat, we need to think about how to optimize. Okay. So what is the optimum way to explore the space? Now you see, this is the rough estimation of the launch cost is around 10 to 15 lakhs per kg of sensor mass. So our approach is to optimizing each building block of space exploration in terms of their efficiency. So in cascading manners, if you sensors, spacecraft structures, and launch vehicle structures. So as a technocrat, we need to think how to reduce, how to optimize without any compromising our objectives, how to optimize the space structures so we can send a large size of space antenna. So as a technocrat, when we think about this one, so this is a multidisciplinary scenario of antenna system designs. Mechanical design involved, thermal design involved, materials and process, and radio frequency design. So this is the mechanical, thermal, electrical triangulate course. This is payload requirement, environmental testing, and antenna requirement. So this is a multidisciplinary area, not only mechanical engineer, not only electrical engineer, not only electronics engineer, but everyone has some contribution is required to design complete space antenna. So this is the multidisciplinary where it is required. Suppose mechanical interference, real states, then power availability, propulsion capacity, thermal control capacity. Then as a design specification, RF requirement is radio frequency, mechanical requirement, thermal requirement. Okay. Environmental and test requirement, reliability, safety, launch environment as a mechanical, orbital environment, thermal and radiation. So every part we need to study. Now, all these things we need to study on the ground station. When we launch on the orbit, then it is not in our hand. Okay. Mission will be fail or maybe success. So before going to launch any space shuttles, everything we need to study, even check every point we need to check at a ground stations. And that's why the inflatable structures is required. And what is inflatable structures and why it is required? As a layman, I will tell you, inflatable means what? Inflate it. Okay. So inflatable structure, that means, even suppose I will give simple example as a layman, umbrella. So if there is no rainy season, then umbrella is in folding conditions. Okay. And you have to pack it in your wardrobe. But when we utilize this umbrella in rainy season, so just you have to pick out and open it, and it will be inflate. So when inflatable, this umbrella will be inflate when it open. Okay, so you can protect yourself against rain, heavy rain. Okay, so when the umbrella will be open, so their cloth, the parabolic shape of cloth will properly open it. Otherwise, what happen? You cannot protect yourself against the rain. Same thing, suppose parachute is another example of parachute of this inflatable. If when you jump it and if parachute will not open, then what happen? Maybe accident will be occur. So properly parachute will be open is essential when you jump it. So how to open? There are lots of mechanism involved, and when it is open it, so there is no requirement of any wrinkles, crease, tightening, okay, proper shape. So everything we need to study. The same thing if we are working on inflatable space structures, okay, so everything is study, or it is essential to study everything. Otherwise, what happens when inflatable structures, when open in the orbit, when we launch the space shuttle on the orbit and it will be open and is not properly open, then our mission will be fail. And our mission will be fail. There are lots of energy, economy, everything involved in the space launching program, space shuttle program. So inflatable structures is very much important in coming era on a space application point of view. So here I will explain why it is required, what is the importance. So you see the motivation of these inflatable structures from a balloon, our football. What is the football? When you are utilizing, you can compress air, you can push it and it will be inflate. Otherwise, it will be in folding condition and put in your cupboard. This one is also, you see, parachute. So you see, when it is open, so proper shape is required. So how to maintain this shape? So all this technicality we need to study as a technocrat. So this motivation, based on this, we have started our journey from since 2005. As I told you, with Mathur sir, I have contacted, and this concept comes from the Mathur sir only in 2005. So here, why the inflatable reflector of inflatable technology is required in the space mission? Because if you compare the solid reflector and inflatable reflector, so there are some limitations of the solid reflector, because solid reflector has there is no any what we can say solid reflector, rigid material, rigid reflector. So there are large space and volume required, mass penalty to launch vehicle, complexity in the deployment because it's a solid, number of components needed much higher as compared to inflatable structures or inflatable reflectors. Higher packaging efficiency means you can fold it on ground station, and when we launch in the orbit, it will be inflated. So higher packaging efficiency, low on board volume required. It's lightweight. It's a very lightweight. Okay, so as I told you now, the costing is involved in per kg of mass. So the lightweight is essential. So lightweight, so low production cost and high strength and stiffness per unit. And that's why inflatable technology is the next logical step in progress on the satellite design and construction. So this inflatable technology is much more important in satellite. Not only satellite, even in DRDO, people also working. They have developed inflatable hospitals also. In now this coming situation, this pandemic situation, if emergency, some hospitals is required. So inflatable hospitals, you can easily open it and you can easily launch it. So the inflatable technology is much more important, and in India as well as other countries also. So what is inflatable structures? Here I am talking about on the space point of view, space application point of view. So what is inflatable structures? Inflatable structures are structures made of flexible outer membrane or fabric. Because flexible outer membrane or fabric, that because it is in ground station, it is in fold conditions. It is in fold condition. That means just is a membrane of fabric, just like umbrella cloth. Okay. So thin materials, the Kapton, Kevlar, Mylars, these are the space qualified materials. It is used in this inflatable structures. So inflatable structures are made of a flexible outer membrane of fabrics that is filled with gas. So when it is required to open it, you can fill the gas, and then the gas gives the shape and strength of the structures. The gas will give the shape and strength of the structure. So proper shape is desired to achieve the proper shape. Proper strength is required. So all this technicality we need to study. So in inflatable structures, this is the inflatable space antenna. This was maybe NASA, they have launched in 1990, but somehow it was failed. So the main component of inflatable structures is one is a reflector. This is the reflector, this part. This is the reflector. The reflector is a multiple gore reflectors, because we are talking about the parabolic reflector or plane reflector. So parabolic reflector, multiple gores, you have to cut it and paste it, and you have to make a parabolic shape. So one important part of inflatable structures is a parabolic reflector. Second one is clear canopy to maintain the gas pressure. So this backside, this one, this is the clear canopy, or canopy is attached with the reflectors. Then inflatable struts. So this is the inflatable strut, this one. Okay, this one is the inflatable struts. So when it will be inflate, so the strut will be inflate, the gas will be passed through this inflatable strut, then torus, and then reflector. So inflatable strut, then inflatable torus, this part, the ring part. I will show one by one component because we have studied all this part. So inflatable torus, this support the reflector canopy. Then canisters is a much more important part where the inflatable structures is packed. This part is a canisters where all these parts are compact and it will be packed on the ground station. Okay, and when we launch it, so one by one part will be inflate and open in proper shape. Inflation subsystem is also required, important. So high pressure nitrogen gas storage, sensor valves and regulators. So these are the main components of inflatable structures: reflectors, inflatable struts, torus, and canisters. And inflatable structures is also 3 types of structures: continuous inflates, rigidized inflatable structures, and single inflation. Continuously inflate means inflation means what? You have to inflate it by external source, by air, by gas. Okay, so continuously inflate is one of the structures. Second one is rigidized structures. Rigidized, that means rigid after inflating. Suppose if you open the umbrella and again umbrella comes back in an original shape, then what happens? Same, you cannot protect yourself against rain. So after opening, it will be rigidized is also much more important. So how to rigidize? Presently, we are studying on this rigidization. We have received the one project from the SEC ISRO, and presently we are studying on this rigidization of inflatable structures. So continuously inflated structures, rigidized inflatable structures, and single inflation structures. The inflatable structures material is a composite as the support structures and polymer as a inflatable structures. It is used in the ground, airborne, in the space applications. So these are the most important part of inflatable structures. And why it is required? If we compare, okay, what is the potentials of inflatable structures? You see the main potential low cost structures is very low cost, because you see in ground station is in compact model or compact form, so not required more large space. Even if you want to utilize large reflector, large size antenna if you want, so with the help of this space inflatable, you can easily any size of space antenna you can utilize. Then high strength and stiffness per unit mass, high mechanical packaging efficiency, easier to store and transport, because it is in compact model, so you can easily store anywhere. There is no required large space. You can easily transport it, and obviously it is in compact model, so it is low weight. Okay, and when we compare with these rigid structures, then you see if we compare on the point of weight, so half the weight. The rigid structure, whatever, suppose rigid structure has 100 kg weight, so inflatable structures are 50 kg, 40 to 50 kg. So you see 50% weight is reduced, so that directly affecting in your cost, okay. So half the weight, volume is less than 1/100 of the rigid structures when in packed complete. So in canister, when it packed, so volume is less than 1/100, means you see there is nothing. Okay, when in packed condition there is volume very less, then cost of inflatable structures is almost 1/10. Cost of inflatable structures is almost 1/10 when you compare with the rigid structures. Means 1/10 means too much, because if you are talking about 1 kg weight on per kg is 10 to 15 lakh. If you see and if you compare it, the weight of the space shuttles on these tons, so this directly lot of costing we can reduce it. So these are the potential features of inflatable structures, and that's why it is used. Some literatures I have found the inflatable structures development in past. So eco balloons, Goodyear inflatable structures, controversial inflatable structures, inflatable antenna experiment. In NASA, people have tried in past. Then in recently, inflatable heat shields, inflatable solar array. In futures, Trans-Hub project, space solar power system, manned mission. Now this is our the Gaganyaan, our prestigious mission Gaganyaan. This is a manned mission of where some astronauts will also go to the space with space shuttle, and then they will come back with the balloon. Okay, so the manned missions. In everywhere, this inflatable technologies is very useful and essential when we are implementing in our space missions. There are different inflatable structures you see, and there are a number of inflatable structures available in the literature. The inflation system, you see, this is the inflation systems, heat shield. This is the global aerospace available. This is the ring inflated, this canisters strut. So now, when we are talking about the inflatable structures, so we cannot easily implement it. There are lots of challenges in these inflatable structures also. Their first is lifetime. How much life it will be sustained on orbit. Then deployment technique, how to deploy is also much more important. Okay, suppose when you open in the umbrella, so if you observe in umbrella, there are lots of rods are attached with the main roads. Small thin rods are attached with the main road. And if you are open it, if you not properly open, then what happen? It will be not properly open it, and you cannot protect yourself. So deployment technique is also much more important than structures and environmental interaction. As I told you, rigidization technique, how to rigidize. Then dynamic modeling of membrane, means membrane structures, because if you are talking about the fabric, because the membrane, what is membrane also I will explain you here. So dynamic modeling of membrane shape inaccuracy, inflation system, accurate pressure control. These are the challenges on a mechanical point of view. As I am mechanical engineer, I am teaching, I am involved in the mechanical subjects. So from mechanical point of view, if you observe, these are the challenges, and we have started to solve one by one with the help of the Mathur sir also. So first we have completed dynamic modeling of membrane, and we have filed 2 patents. Our first project under Respond, so where we have developed membrane modeling, membrane shape inaccuracy. Presently, we are working on the deployment technique and rigidizations. So we have successfully completed this part, and presently this is going on. So there are the different challenges we have to face when we are implementing this technology, inflatable technologies. So now you see, this is the inflatable antenna which I told you, the inflatable strut. This is the inflatable strut. This is the clear canopy, antenna canopy, this one. This is the reflector, antenna membrane reflector. So membrane is a thin material, just like paste. You can easily fold it, you can easily twist it, you can easily tear it. Okay, fold it, you can easily fold it. So this is the reflector, the membrane reflector, we can say. This one is a torus, and this is the canisters, where all these components will be packed in this part. This is the canisters, where all these components will be packed in this. So now you see, this is the reflector. Presently we are working, IIT Roorkee is working on this reflector structures and torus. Okay, so the reflector structures and transparent canopy used to form a closed cavity so that the inflation gas will put tension on the 2 membranes. So now I will show one short video how to inflatable technology it works. You see this video, you can easily it's visible, sir. Video is visible.
The video is not visible if you're playing.
Not visible. Okay. Okay. Now it's visible.
Yes, it is now.
Okay. It's visible, sir. Video is visible. Now you see how it will inflate. Now you see from canisters, the inflatable struts first inflate it. So inflatable struts are inflated, then after it will be goes to the torus, and then finally reflector will be inflated. So initially, if you have seen, this is compact model, and then after, now you see the inflatable struts are start to inflate. This is the inflatable struts first going to inflate it. Now going to start open to the reflector with the help of torus. So first inflatable strut will open, then with the help of this torus and then reflector will open. So now you see there are lots of technologies are involved. We need to research, we need to study how to pack, how to deploy, how to inflate, how to rigidize, how to get the shape accuracy, how to get the wrinkle free area. Now you see this is completely inflate with reflector, torus, and strut. Okay. So if you want to success it, if you want to succeed it, if we need to study all this technical part, how to inflate, how to rigidize, how to maintain the shape control. Okay, you see, this is the reflector, you can easily visualize. So this is the short video, you can get the idea how the system is work, how to inflate it. Okay, so now we are going for the various inflatable membrane shape. So you see, this is the circular membrane, then triangular membrane, rectangular membrane. So we have studied all these mathematicals and we have achieved the results, and we have compared these results with our own experiment in our lab. We have developed a smart material and structure labs under RESPOND project, and thanks to Mathur sir also. The first RESPOND project was sponsored from the ISRO. At that time, Mathur sir was a group director. So these various membrane shape we have studied. You see, this is the very thin material and transparent material. Okay, if you observe this very thin material, so you can easily fold it, you can easily pack it. Okay, so we need to study when you packed it and when we open it. Okay, so there is minimum wrinkles, minimum crease interaction. Okay, because RF zone means radio frequency zone. If you are talking about the radio frequency zone where the signals will be receiving and signals will be transmitting, so where there is no wrinkles is required, there is no wrinkle, that means complete surface accuracy we require. So all these parts we need to study, and obviously when we pack, when we fold it, so if simple thing, if you fold your page, so when you fold your page, the crease may be occurred, wrinkles may be occurred. So when we open it, so this part will be a wrinkle free, crease free. We need to study. So this is the various shape of inflatable membrane shape. And what is membrane? So membrane has no compression or bending stiffness. Therefore, it has to pre-stress to act as a structural element. One is a structural element. So when you develop some FEM code, when you maybe work in ANSYS or Abacus, okay. So when you make a model, so it's a membrane is it's a structural element. Membrane is a high dimensional, two-dimensional brain point string. These structures could be flat plate or inflate curved panels, but they cannot resist compressive loads. Tension is only load path is available. This is the technical part. Okay, then thin membrane and thick membrane. Thin membrane is deflection is greater than thickness, and thick membrane is deflection less than equal to thickness. So after this analysis, we have developed a mathematical model of the membrane to study the wrinkle, shape control, wrinkle control. So adaptive control, what is adaptive control? Why it is required? So control the undesired shape, wrinkles, structural vibration, and surface error. That means if you want to control the shape, control the wrinkles, all these things is essential. And what is adaptive control? Adaptive control, that means once you launch the space shuttle in orbit, then it's not in our control. So in orbit, it will be open, it will be gain the shape, size. Okay. So according to the environment, it will be gain their shape, it will be control their shape, it will control the wrinkles. Okay. This is known as a adaptive control, and we have developed adaptive control technique, and we have filed the patents. So you see, this is this is our lab photograph where this Kapton material we have received from the Vikram Sarabhai Space Center through Mathur sir also, and we have putting this piezo patches. I will explain you what is piezo. So with the help of this, we can easily control the shape, wrinkles, vibration, and surface error. Surface error is much more important because suppose if you are talking about 1.2 meter by 1.2 meter, okay, that means 1 meter by 1 meter is your RF zone, radio frequency zone, where it is completely free from the wrinkles, free from the trees we need to study, where the signals will be receiving and signals will be transmitting. So this is the adaptive control technology is required because of to control the shape, control the wrinkles, structural vibrations, and surface error. And how to control it? So with the help of smart materials. Okay. The materials is smart materials. These materials are utilized PVDF, polyvinyl fluoride, MFC, microfiber composite, shape memory alloy, PZLT, piezo patches we can say. So these are the materials have their own characteristics. They have they have sense it and actuate it. So they have own characteristics. That's why it is known as a smart materials. And it is used, or it will be used in our mission. With the help of this PZLT, we can easily control the shape, wrinkles, vibrations. Presently, we have utilizing this shape memory alloy for rigidization process. Just trial and error we are going to study by utilizing this shape memory alloy for a rigidizing point of view. So it is going on. So this is a much important material where it will be used to control the wrinkles, vibrations, control, and the mechanical strain when subject to electromagnetic field and vice versa. That means it will be actuate and it will be sense it. So this is that's why it's known as smart materials. So usually this is a layer, piezo layer, and some structures you can easily paste layer as well as the patches. Now you see the smart structure. That means now when we utilize these smart materials on any structures, and it is known as a smart structures. Any smart materials when we utilize, there are even in lubrication also MR fluid, ER fluid, micrological fluids, electrological fluids, MR, ER fluids. What is this? It's also a smart fluid. It is utilized in the lubrications for reduce the heat temperature. The smart structures, this is the sensors, actuators, and control. So same material, this much smart materials, it will be actuate, sense it. This is a closed loop systems, closed loop control systems. And that's why it is known as a smart materials. And these smart materials we can utilize in the any structures. It is known as smart structures. This is some piezoelectric material characteristics. Then magnetostrictive materials, electrostatic materials have some characteristic direct effect and reverse effect. As I told you, it will be sense it, means it will be actuated and it will be sense it. So if you see here we have put piezo patches. So one piezo patches is utilized for the actuate it, and another piezo patches it is utilized for the sense it. So we can easily sense the vibrations in data acquisition systems. So you see, this is some PVDF layer we can utilize in a structures. This is known as a smart structures, you see. So this is the this part, white part, this part is a structures, then bottom part is a actuation, upper part is a sensing. So it will be sense, actuate, and this is the processing unit. We can say the data acquisition systems. So it will be actuated, it will be sense it. This is known as a smart structures. This is known as a smart. This is a maybe piezo layer or PVDF layer. Any smart materials you can utilize as per your requirement, as per your application. So this is the smart materials. So now we will go for this technical part. So first we have studied the wrinkle analysis. Why it is required? Wrinkles means, if you see the inflatable structures on ground station is in the fold condition. Okay. And when we inflate it, so when inflated, so it is required wrinkle free area. So we have studied wrinkle directions, wrinkle regions, wrinkle amplitude, wrinkle wavelength, number of wrinkles, wrinkle free area, and RMS error. We have studied. And by considering the external factors, Young modulus, Poisson's ratio, and thickness, then material layer with direct deposition, material layer with adhesive, layer composite, and this is the imposed factors. Anchor size, number of anchor point, age trimming, aspect ratio, scale factors, all these things. So one of our research scholars, Dr. Satish Kumar, have studied all these things, and presently he is an assistant professor in MNIT Allahabad. So we have developed a smart material and structure laboratory in our mechanical department in Respond project. So this is our setup, the Kapton material. This is space qualified material. You see, so you can observe this is a number of wrinkles here. You see, these are the wrinkles here. We have considered as a triangular membrane. Sorry, the rectangular membrane we have taken, and first we have studied the wrinkles. So we have studied the analytical as well as experimental study. Okay. Here I am not going to much more depth in the technical point of view because lots of equations and modeling, but brief I will introduce how we have controlled the wrinkles. So this is the analytical as well as experiment. As I told you, we have developed mathematical model. We got the results, and same results we have compared with our experimental setups. So this is, you can observe these wrinkles in mathematical, even experimental also. Okay, this is the wrinkles. This is the wrinkles you see. So first we have done for getting the confidence, we have done small experiment on in here. This is a laser, Polytech laser vibrometers, where we have done 0.5 meter by 0.5 meter. And after getting the successful results in this one, then after we have developed 1.2 meter by 1.2 meter setup in our smart material and structure labs. So here, this is the Kapton membranes, laser displacement sensor. With the help of this laser displacement sensor, we can easily measure the wavelength, wrinkles, wavelength, amplitude, magnitude. The piezo actuation sensing unit is here. So with the control the wrinkles, it is required to stick the piezo patches. Then here Kevlar strings we have utilized. This is space qualified material for hang on these structures. So here we have done experimental for prototype model by this membrane we have attached. Even we have studied some thermal temperature. So in summer we have putting some heaters, and we have increased that our lab temperatures around 70 degree to 80 degrees centigrade. We have increased it with the help of this heater, and we have measured the wrinkles also. So wrinkle analysis we have studied. Then after shape control analysis, okay, the shape control is also much more important because again, I will give you example. Umbrella, if you open it and if you are not properly open, the cloth will not properly open in parabolic shape. Then what happen? You cannot protect. Same thing in inflatable structures is not properly open, then your mission will be failed. Your objective will be failed. So shape control is also much more important part. So shape selection we have taken as a parabolic membrane and planar membrane where we have studied it. And parabolic membrane and plane membrane we have taken. This is, you see, this is the planar reflector and this is the parabolic reflector we have studied, where we have considered the control the wrinkles for edge trimming, punching, and anchor point. So if you at each and every corner, you see this is the each and every corner we have tie up. Okay, that means you can easily reduce the wrinkles. You can usually reduce the wrinkles. So same thing on a square membrane as well as here a rectangular membrane. Sorry, circular membrane. So we have done mathematically as well as experimentally. So this experiment we have done in 6 gores and 12 gores we have developed. This is a cycle tube. Another example I will give the cycle tube. Okay, so the cycle tube when we are not in inflate. So cycle tube is completely in packed model in polyethylene bag. But when we open it and when we insert the air, so it will be completely open and in circular shape. Are you getting my point? So same concept here. It is in packed model, but when you inflate with the help of air or with the help of gas, so we require proper shape and size. We need proper shape and size, because if we are talking about the space application, so if it will not open properly, then as I told you, the mission will be failed. So we have parabolic reflector, reflector we have considered by 6 gores and 12 gores, and numerically also we have developed this model and we have compared the result. The shape control analysis is also much more important. Then we have filed 2 patents, as I told you, wrinkle and shape control. So we have developed the adaptive shape control mechanism from a planar membrane structures. Planar membrane structures we have developed. This is the completely control mechanism where microfiber composite MFC we have used the string to be attached the membrane here. This is the load cell and this is the adaptive support devices. This is the load cell, load sensor we can say. So according to the environment in orbit, it will be directly change or control the shape. You see, this is the membrane clamping devices. So this is the membrane RF zone where we are not going to disturb anything. But this part, yellow part, where we have putting this string attached with this torus. And this is the complete mechanism, adaptive control mechanism, hardware and software. So we have filed this patent in 2018. Then second patent we have filed in thin membrane based singly curved cylindrical parabolic reflector. So this is the singly curved parabolic reflectors. We have, this is a part of our inflatable studies. So presently, which we have done it. And one of our research scholar I told you, now presently is in MNIT Allahabad. He done lots of work and based on this, he got opportunity in Allahabad, in the Central Funded Institute. Now presently the work is going on folding and deployment analysis. So as I told you, folding is much more important. How to fold it so you can easily inflate it without crease, without wrinkles. So there are lots of folding technologies, jet fold, origami folding technique. There are lots of folding technique is available. So which one is suitable for our application point of view? The selection of folding patterns, Moriai Ori patterns. Our one of the research scholar, Mr. Hemant Sharma, presently is working on this topic. Mathur sir is knowing very well him. and he has already published 2 papers, and 2 is under review in Advanced Space Science elsewhere, another in Springer Journals. He already published 2 papers. So how to fold it is also much more important. So modeling of folded beam, then deployment simulation, deployed shape, deployment strain, and deformation analysis. So this again is a technical part, mathematical modeling and everything. So this folding and deployment presently is going on. So you see this video, I think is actually this is the minimum deformation patterns. It is not, video is not working. So this is folding patterns, and it will be inflate. It will be inflate. So experimentally and analytically, we have compare our results, folding sequence, how to fold it, experimental deployment, deployment simulation, and so we have considered first boom, deployment of boom. So if you are talking about the inflatable strut, so first we have considered as a boom. So boom, how to fold it. So we have studied this. Actually, this is the video, but is not work it. Okay. So this is the boom we have unfold it. This is our experimental setup where we have inflate completely a boom. Then this parabolic membrane, how to make a parabolic shape is much more important. The developing of the inflatable parabolic reflector from planar membrane. Okay. So first we have consider the ideal surface. Ideal surface like this one. This one. So ideal surface, trace release, then initial surface, generation of cutting lines, subsurface means is flattening, then planar gores, seaming, every gores. This is the one gore, second, third, every gore we have to cut it, then it will be stick it will be seaming, and finally you can get the desired shape of the parabolic. You see, this is the one gore, second gore. So all these gore, first gore, second, third, fourth, all gores we have to attach, and finally we can get the parabolic shape. And this parabolic shape here, we have attached with this torus. We have considered as a torus, like this one. So this is the reflector, and this is the torus. So final. So we have developed this parabolic membrane, and we received the lots of results also. I will not show the results here, but the how to develop parabolic membrane, inflatable parabolic membrane is much more important. Inflatable parabolic membrane. I will show the video also. So this is the results of number of gores, 16 gores, 24 gores, 30 gores without seaming, and the RMS error is reducing without seaming. So RMS error reducing, that means wrinkle free we are getting, shape control we are getting. So numerical analysis of this parabolic membranes. You see, this is the experimental results also we have considered. 6 gore, 12 gores, okay, RMS error. So a parametric analysis is used to demonstrate that the magnitude of RMS error depends primarily on the number of gores. So if the optimal number of gores is determined that they produce the highest shape accuracy. Are you getting this one? Why we are studying? Because of the shape accuracy is required. The optimal number of gores is determined that they produce highest shape accuracy. And the RMS is also affected with seaming taps and central cap. So central cap, that means here, this is the central cap. If you see here, this one, this part, this is the central cap, where with the help of this, all these gores we have to tap it. To validate the effectiveness of the proposed analysis method, 0.5 meter antenna reflector model is designed, manufactured and assembled for a ground demonstration and testing. So we have ground level, we have studied all these things. So you see now this initial phase of prototype model is studied. This is the parabolic membrane. Same, the video is not working here. So this is the parabolic reflectors we have developed. Now you see, this is the cycle ring, tire tube ring we have utilized as a torus. And then after we have developed, we have make it inflatable torus here. Okay, so inflatable torus, how to make is also one technique. You cannot easily inflate and put it. Okay, if you're observing one component, one part, we have considered it and we have sticked it. So we can easily fold it. And when we inflate, so it will be easily inflate. And then after this reflector, actually this is the video, but it's not working. So how to inflate? Here we have, with the help of compressed air, we have inflated. This is a prototype model. Then after consulting with the ISRO people, we will put in the actual model. So presently this study is going on, parabolic reflector inflators. So these are the topics, means this is the inflatable structures and why it is important. Hope all of you clear this one. Just I will brief presently, as my area is on smart material and structures as well as the vibrations, bearing dynamics. So I have total 6 to 7 projects. Out of 6 to 7 projects, 4 projects is related to the space antenna, inflatable technology. So first project successfully completed. At that time, Mathur sir was the focal person, design and development proof of concept model of adaptive membrane inflatable satellite antenna, completed with the 2 patents. One project is going on, design development of 6 meter and 1.5 planar membrane reflector. This is going on, where this is the inflatable part. Actually, this is also video, but I think it's not working. So how to inflate? So this is the inflatable part. It's working. Another is design and development of proof of concept model, packaging methodology of a gas, how to pack it. So presently we are studying, and safe control is also, it is on pipeline. So this is the 4 projects presently going on in our smart material structure labs. In last 5 years, I have guided 3 PhD completed, only inflatable. Totally, I have guided 9 PhD students and 6 is ongoing, but 3 is on completely on inflatable structures, 6 ongoing, 20 MTech projects, BTech 9 and internship 8 students. International journal, out of 75 papers, 15 papers on completely on inflatable technology, national journals, conference proceeding, and 5 patents. So these are the patents. We are adaptive safe control mechanism of planar membrane, then tensioning connected devices in 2020, then 2020 and 2021 we have filed this 5 patents. This is the experimental setup where we have developed the smart material and structure laboratory at MIT IIT Roorkee under RESPOND project. This lab, so whenever you time, please visit, and you can see our laboratory also. This is our experimental setup completely. This is the Kapton membrane, the wrinkle area we have studied here, wrinkle, safe control, and the rigidization part, then deployment technique still going on. Even I received best paper award in ASME, American Society of Mechanical Engineering. I was presented in 2012, Chicago, Illinois, USA in ASME conference, where I have got best paper award on vibration analysis of inflatable parabolic structure for the space application in 2012 also. So it's a very interesting topic, and there are lots of things, technicality we need to study, we need to explore still. Still we are trying to study, and we are approaching for inflatable structures. Mathur sir is also helping on this area. So thank you all of you, and hope all of you enjoy this topic. If you have any question, you can ask me. Thank you all of you.
Yeah, anyone having any question can directly ask.
So there are some questions from YouTube and some in the chat box as well.
Okay.
Shall I read them? one question is from Jay Kumar. How is the criticality of an inflatable structure of spacecraft assessed for its certification? How life assessment is done?
How lab assessment?
Life assessment.
How lab assessment?
How life assessment is done?
Yeah, so that's why I already saw the challenges in still it is unexplored area. If you see these challenges, lifetime is still unexplored area, so it is required. And when we are approaching, so we consult with the ISRO peoples, and definitely we will study this one.
Sir, I have a question. How do you deploy the gas? Like how is the inflation process done? How is the gas stored? Like I was a little curious. In space, you don't have a tank of gas, so how does
Exactly. Well, actually, still we are going to study now. Some small cylinders of gas will be attached with this system, so it will be directly inflated. So still it is unexplored area where how to explore it, and that's why this inflation system, you see, this is the challenging of inflation systems, is still unexplored. So
the people they have carried is with the gas, and once only you can fill up the gas. They are very small cylinders. Once you inflate the system, then the surface of the structure gets automatically rigidized by ultraviolet rays. So the system, the total mechanism is not reversible. Once the antenna or any structure is open in space, it is inflated and rigidized. Then it cannot be revert back.
Thank you, sir.
That is the technology.
yes, sir.
Sir, apart from these, there are no direct questions for the present speaker on the
How
chat
to?
box or on YouTube.
Okay, from YouTube also there is no question. No question from here. Okay. Then you can close.
Thank you, Mathur sir. Give me opportunity to interact with the audience.
Thank you, Upadhyay, for accepting our offer, sparing your important time. I know you are quite busy nowadays in the campus because of the COVID and other things.
Yes, sir. Yes, sir.
And in spite of that, you could spare more than an hour. And especially all of us, are trying to educate our young Indian engineering students. That was the aim on National Technology Day. So we should share the knowledge with the young generation. And Dr. Sanjay Upadhyay, Dr. Vishak Bhattacharya, all of them, they readily agreed my request and agreed to deliver the talks. It is up to the student. They should try to learn maximum from this. There are many students, those who simply run after the certificates. Now, getting a certificate is not a problem. No, until unless you get the knowledge, certificate is of no use. You take the certificate, go for some interview, and if somebody asks a question, what you learned from this particular awareness series, what is the inflatable structures, and you are not able to answer, it is of no use. So it is a good opportunity to learn and interact with all our IIT's professors. They're all 5 IIT's professors are taking part in this and experts from the industry. So this is a good opportunity for the young students to learn out of that. So thank you, Dr. Sanjay.
Thank you, sir. Thank you.
For that. Thank you very
Thank
much.
you, sir.
Today, next talk we have, I think this is the last talk of today's program, is by Dr. Vishak Bhattacharya, and he has already joined. Welcome, Dr. Vishak.
Thank you. Good afternoon.
Thank you. Good afternoon. And thank you very much for accepting our offer for delivering a talk on the National Technology Day. And
good afternoon, Professor Vishak Bhattacharya. Good afternoon.
Good afternoon. Good afternoon.
Yeah. So we have got a very long evening with Dr. Vishak Bhattacharya. When I was in SAC, since long we're interacting with him, and he's a professor, senior professor rather in a mechanical engineering department of Indian Institute of Technology, Kanpur, and he's working on a number of projects with ISRO. And he was associated with the space technology cell also. And the first project now, engineering project which was cleared at Space Application Center under RESPOND was on a smart antenna system, and which was submitted by Dr. Vishak Bhattacharya. Successfully completed that project, and after that our team evaluated all the RESPOND projects. I think that project got the maximum marks, maximum rating in that time. And still, Vishak Bhattacharya is working in the field of smart materials and systems, shape memory alloy and piezo system, how we can change the shape of the structures in space using these alloys. And this is a very upcoming subject. Very few academic institutions in the countries are working on this particular subjects. Earlier we used to, but nowadays some of the wires have been are being manufactured by National Aerospace Lab as well as Vikram Sarabhai Space Center. So the material wise not a much problem, and there are many dealers who can import this material and supply it. But understanding the properties of the smart materials, especially shape memory alloy and piezos, and how to use into our engineering projects and develop smart systems, it is not so easy. Dr. Vishak has presented a lot of papers and he has got a number of patents to his credit, and he is a member on so many committees, and he was a member of our journal which was being published by Ahmedabad from SSME, Space Society of Mechanical Engineers also. So without taking much time, I'll hand over to Dr. Vishak for his talk.
Thank you, Mathurji.
Thank you, sir.
Thank you, Mathurji.
Thank you, sir.
So I will just share my screen. And I have a little high number of slides, but because I thought that, I would like to give you the glimpses of all the smart materials that we are using in different contexts. So there are a lot of slides related to each one of them, which will give the audience an overall idea of different aspects of the works related to smart materials. And because this is the last talk, so I hope you would not mind if we overshot by a few additional minutes. But please stop me anytime if you want any clarification, or if you think that the time is up, just please let me know. So with this, I will just start my talk. And once again, I would like to say that this is a very good and very timely endeavor on the National Technology Day. And I will talk about smart materials research, particularly in IIT Kanpur, with two different branches of application in mind. One group is called soft robotics, because soft robotics is coming in a very big way now in many applications related to, let's say, social robot development, that is robots that works inside society, or related to the development of robots for space applications, where weight penalty is something which has to be taken very seriously. Soft robotics has come up in a very big way, and smart material is an integrated part of such soft robotic system. And the other group of applications that I will talk about is related to intelligent system design. So if we start with these, first of all, I want to give you some motivation towards this direction. And the motivation for me is the octopus. I hope many of you have seen this year's Oscar-winning documentary of My Octopus Teacher. If you have not done it, please, you should see it. Octopus is a fascinatingly intelligent element which has about 500 million nerve cells, almost at the same level as a dog or a cat, but it is an invertebrate and it is just little above the mollusks like the snails. So it is something which is like, it's a kind of a wizard, it's a bizarre thing that how can an animal which is so much down in the scale can possess so much of intelligence in it. And one of the such intelligence, intelligent behavior that it displays is when it tries to escape. So that's what I want to show you in this video. So you see here that the lid is getting closed and an octopus is kept inside this system. And the arrows matched, which means it is properly tightened. Now you see after some time what the octopus does. So you see it starts to feel and it starts to move the lid and check that in which direction it is opening up. It has all the feelings in its arms itself. It has all the intelligence in its arms itself. Much unlike us, it has no centralized brain in that sense. And with the help of these arms, it is understanding which way the lid can open up. And through a bit of trial and error, it has understood that. And also, you need to give a bit of a normal force, and that also it has understood. And you see, it is able to escape from this situation as if in a very effortless manner. Now that is something that is unbelievable, and so far there is no robotic system which can actually simulate or emulate this type of behavior of an octopus. So this is one of my inspiration, that can we develop soft robotic system like the arms of an octopus, which can actually feel the environment and change its shape, change its behavior in terms of the transmission of force, moment, etc., and plan for escape and escape strategy. Now, people from 2012 onwards, people started working on shape memory alloy wares, which is braided inside a polymeric network. You can see the SMA braided inside a polymeric network, which can partly emulate this kind of a behavior of an octopus limb. But if you consider the capability of an octopus limb in terms of that, it can develop textures which can match the environment, it can sense the pressure, and accordingly it can change its shape. It can even plan for a very fast escape if needed, with the help of some kind of a special ejection of an ink. All these things are still beyond the capability of a robotic system so far. Now, this brings into context that how can we develop an artificial intelligence system, and what are the different classifications or grades of such artificially intelligence system. The crudest, of course, of them is where the structural coupling is there between an agent and an environment. An agent can be a robot. So where there is a simple structural coupling between the agent and the environment, let's say that a robot is moving on a surface, and the surface, because of the gravity, It is applying force on the robot, and the robot is trying to overcome this force of gravity. So it has a simple structural coupling. If there is historical embodiment, then it also should have a kind of a storage of the history of agent environment interactions. That means how, if there are some obstructions in the path and you know about it beforehand, the history of it, then what has to be the path of movement so that you get least amount of resistance, etc. There is physical embodiment of intelligence that people are today talking about. For example, the embodiment of motors, with the embodiment of actuators, with the embodiment of sensors. So these are the physical embodiment. And with some more sophistication, we can bring it like an organism-like or a bodily form. So organismoid embodiment, which will have quite a few degrees of freedom, such that this entire sensory motor capacity can actually mimic a living body system. And of course, our final goal is to reach towards organismic embodiment of autopoietic system, which would work just like a living system and think like a living system. Now, in order to build up this type of a system, we would see that smart material is an inevitable part of such a design. Now, let us look into one of the robots, a humanoid robot, which is from Honda, and which is a very famous Asimo robot. Just let us see how an Asimo robot works. You can see that it is bringing a trolley in order to serve some drinks. It is a very famous Japanese humanoid robot. You can hear the sound of the motors of various degrees of freedom. Step by step, it is actuating. And you can see that how it is shifting its stance very carefully so that it does not obstruct or topple the glasses. Now it is visually processing the glass and the bottle because it has to serve a drink. And then you can see how it is grabbing with its 5 fingers the bottle, and then it is going to apply the torsional force in the proper direction to open it up, very much like the octopus limbs that I have shown you earlier. So it is opening up the bottle. It has understood the exact amount of force that is needed or the torque. Now it has to hold the glass with a much lesser, because it's a styrofoam glass apparently. So the torque has to be controlled. The gripping force is to be controlled. And it seems like a glass of Japanese tea that it has poured into and which it is going to serve. So that is the Japanese thank you for receiving the whole thing. And you can see that the successful level of development of a humanoid robot, Asimo, and it has 34 degrees of freedom that helps it to walk and perform tasks very much like a human. And it is made of lightweight materials, not a soft robotic material, but materials which is like magnesium alloy structure, combined with powerful computers and 34 motors. That gives it this kind of a humanoid-like appearance. So these are some of the data, and you can see that with all this intelligence, it can work at most for 1 hour in today's situation. Now, how many degrees of freedom we have if you have to develop a truly organismic robot? You need to have 57 degrees of freedom at least, whereas this Asimo robot is having only 34 degrees of freedom. And that too, it is of so heavy weight that it can only work without power supply for 1 hour only. And its weight is about 50 kg in a 4 feet height. So you can see that the limitations of these designs. And hence, for a better organismoid embodiment in robotics, we need to think of muscles. We cannot really think of motors. Motors has to be substituted by muscles, which will be much lighter in weight, yet which will be able to generate the desired level of torque in order to operate the system. And I had given you that octopus example. Now, if you look at any of the muscles, so to say, and you can see that the force level in terms of the pressure per unit, force per unit area, the pressure, the muscles are somewhere in this region, which is close to silicon rubber, something like 10 to the power 6 Pascal, or so to say megapascal level. On the other hand, the robots, like the aluminum alloyed robots, they can give a much larger force, something like in the gigapascal level, but they are heavier in weight. So you can actually compromise on this force a little bit, but you can reduce the weight so that you can develop something which is more organismoid in nature. People have tried many different variations like caterpillar-inspired locomotion, then multi-gate quadruped, active camouflage system, and robots which can work in hazardous environments, worm-inspired locomotion, then particle jamming-based actuation, rolling powered by pneumatic battery, hybrid hard-soft robot, snake-inspired robot, jumping powered by internal combustion, and then manta ray type of robots, etc. Now, one of the things that is required in order to develop the muscles is actually to have a kind of a compliance system. So initially, people have worked on pneumatic artificial muscles, which works on compressed air system. But however, this needs a bulky storage tank to carry with you. So that is something that will give you a large weight penalty. So instead of that, we have worked on something which is like electroactive polymers, which are, I will later on talk about such polymers, that how they work, but I will try to give you a glimpse of it here. So you can see that these polymers are quite flexible and you can apply voltage at one end and the polymer can get bent and grip an object. And I have also shown that you can even develop, instead of a single link system, open link systems, you can develop a closed link 4-bar mechanism also with this kind of polymers. And then you can develop fantastic compliant grippers out of it. Now, all these things need smart materials to be in place. And what are these smart materials? They are broadly known as functional materials, which has the capacity of interchanging the energy, let's say between thermal energy to mechanical energy, or electrical or magnetic or sound energy to mechanical energy. In every case, the common currency is the mechanical energy, because you have to develop some kind of a locomotion, some kind of a force generation or a torque generation. So the currency is mechanical energy, and this you can, as you know, the energy cannot be destroyed, right? Energy can only be transformed. So this you can, you should be able to develop by transforming energy from thermal energy or electrical, magnetic or sound energy. And these materials that can do it, they are quite analogous to biological materials because they are adaptive, they have a cellular-like function, Even if you break a smart material, each small part still works. And they have a capacity in most of the cases of self-sensing as well as actuation as well as control. And they are highly embeddable in nature. Now, I will discuss about a group of smart materials depending on which energy they are transforming, like piezoelectric, which can transform electrical energy to mechanical energy and vice versa. Magnetostrictives, which can transform magnetic field, magnetic energy to mechanical energy. Shape memory alloys between thermal and mechanical energy, and electromagnetorheological materials like electroactive fluids or magnetorheological fluids. And all these materials, their smartness can be nicely grouped in this particular table, where these horizontally what we are looking at is the output. So you can see the outputs in terms of current or charge, magnetization, strain, temperature, or light. And the vertical column wise, what you can see is the input energy. So like if your input energy is mechanical and if you get output as strain, then there is nothing smart about it. Any material can show it. But if your input energy is something like magnetic field, and if you get output as mechanical strain, then this is an important smart material called magnetostrictive material, which shows the Joule effect. And similarly, from the electric field to mechanical strain, there is reverse piezoelectric effect, and there is this phase transition for shape memory alloy between heat to strain, and light to strain is the photostrictions. So in this column, apart from the central material, all the others, you are actually applying as an input the mechanical, the non-mechanical energy, and you are getting the output in terms of some deformation, which means this column, the materials here, they actually work like actuators. On the other hand, if there is a mechanical deformation and you get a change in the electrical or magnetic energy, electrical or magnetic field, or temperature or light, then this horizontal direction of the row, this is where is giving us the smart material, which has basically the capacity to work as a sensor. So these horizontal direction, we have the sensors, and the vertical direction, we have the actuators. So different smart materials are actually placed along different positions depending on their capacities in this central group of materials. Now, why we are so much interested on these materials is because if you look at their accuracy, it is phenomenal, 0.01 micron meter. You compare it with any of the motors and other pneumatic and electrical systems, it is far, far ahead. And also the response time, these systems are very fast in terms of their response, 0.1 millisecond. Your blinking of an eye takes something like 100 milliseconds. Within 0.1 millisecond, if something happens, then you can understand that how fast such a system can work. Now, one of the first groups of materials in this direction is called piezoelectric material, in which once you apply the voltage, you can see that there is a change in shape that is taking place. Also, if you apply the force, if you expand or contract the material, you can generate voltage from it. So the material can sense as well as the material can actuate. And this is a material which was developed long before in 1880, but only today we are getting the advanced form of this material, which can show the effect in a very predominant manner. So Pierre Curie and Jacques Curie are credited with the development of it. And later on, Pierre Curie got his Nobel Prize on radiation phenomena in 1903, and where this particular discovery actually helped a lot. And also Gabriel Lippmann got his Nobel Prize on the reverse piezoelectric effect part. So the direct piezoelectric effect is where you are applying the mechanical force and you are getting voltage out of it. On the other hand, for reverse piezoelectric effect, you are applying the electric field and getting the mechanical change. That's what Lippmann predicted through his mathematical model and got his Nobel Prize in 1908. Now we can explain that why such a thing happens by considering one of the special materials, which is a AbO3 or a perovskite material. Like it is a double oxide, barium and titanium oxide. Okay, it's a ternary 3-component structure where the titanium is at the center, and then it's a, as you can see, it's a tetragonal structure, and then bariums are at the vertices and oxygens are at the face centers. Now, such a system, even though they are in equilibrium electrically, but the moment you apply a little bit of pressure, then this titanium at the center will get displaced a little bit. And that little bit of displacement will actually create polarization in the system, because the electrical equilibrium will be lost, and titanium is very strongly, you can see that electropositivity. So it is going to be closer towards some of the these anions, and as a result there will be a charge which will be instantly developed. So there will be an instant polarization in the system. Similarly, if you apply the electric field, then the titanium at the center will jump towards that direction, and that will create a change in the crystal structure mechanically. Now, this effect is observed in lead zirconate family, in lithium niobium, lead niobium family, yttrium magnesium manganese family, and ammonium cadmium family. So there are a lot of materials which shows this type of phenomena, and hence they can be used as piezoelectric material. Now, the constitutive relationship, I'll not go very deep into the mathematics, but I just want to tell you about the direct and the reverse or the converse effect. As you can see that in the direct effect, the electric field can create charges. We know that that happens for so-called materials which are like capacitive materials or dielectric materials. But in this case, if you apply mechanical stress, this X is the stress, you are going to get electric field displacement, or some charge is going to accumulate, and that's what is the direct effect, stress creating electric potential. On the other hand, following the second constitutive relationship, if you apply the electric field and if that generates strain, because stress generating strain is no smartness, it happens in any material. But the application of electric field generating strain, that's what is called the converse or the reverse effect. And that is something which is used invariably for all soft robotic actuator applications. So you can see some of the applications. For example, the desk jet printer.
Voltage is applied to a piezoelectric element. It contracts. A piezoelectric element and a vibration plate form a set. The contracting piezoelectric element moves the vibration plate to generate an inkjet mechanically with no need for heating. Each inkhead contains thousands of these sets, with each one firing precisely the right amount of ink at precisely the right place, more than 40,000 times a second, achieving fine, high-quality printing.
And you can see some other application of amplified piezo actuators, where you can see that the piezoelectric material is at the center, and that is creating so much large changes in terms of deformation. Similar thing you can see in this another type of macro fiber composite, which we use in the laboratory these days, and that also shows a very large degree of deformation in the system. Now, I would also talk about another group of material where magnetic energy gets transformed to mechanical energy and vice versa. They are very high energy density material. You can see a magnetostrictive material where if you apply force, you can understand the energy density.
Yeah.
So you can see the huge amount of energy change that happens in magnetostrictive material, which is basically a compound of iron, and then it has terbium, and also it has dysprosium. These are all rare earth materials. And what happens is that in these materials, there will be such magnetic dipoles which will be randomly aligned. But the moment you apply the magnetic field, then these magnets will actually align themselves with the magnetic field, and that will create an expansion. But remember, whereas for reversal of the magnetic field, you will only get expansion in both the cases. But for electric field in piezoelectric material, you can get both expansion as well as contraction. Whereas here, you are only going to get expansion in the system. Now, similar to piezoelectric material, this effect was also known to people for last 200 years, but it's only recently that people have been able to understand that by adding with iron these rare earth materials of different types, terbium, dysprosium, many other materials like gallium, and all these things people are now mixing with different stoichiometric ratios, you can get a large striction. Magnetostriction means a large strain out of this system. Now this is parts per million, which means 2,400 parts per million parts. That's the level of strain that you can develop in such a system. Now, in order for you to get some kind of an idea of these parts per million, let's say if I consider a rod which is of 100 millimeter length, and then if it shows something like 4,000 parts per million, that means the change will be something like 0.4 millimeter. So it is quite small, but you know, the force, if you can stop this change, is actually very high. And these things invariably works like a butterfly. That means you reverse the magnetic field, you are once again going to see expansion in the system. So reversal of field will not take you to a negative strain, but only to expansion. The first application of such an effect was in terms of some defense applications, where underwater missiles were actually fitted with this system in the sonar system, so that if there is an enemy ship or submarine approaching, then there is a change of pressure, and that change of pressure will create a change in the magnetic field. And that's the way to be able to hear the presence of some enemy vehicle. Now, there are different magnetostrictive effects like Joule effect, Whiteman effect, magnetovolume effect. These are all reverse effects. That means this is where you are able to develop actuators by application of magnetic field. If you develop a linear expansion, that is the Joule effect. If you develop a torque, that is Whiteman effect. If you develop a change in volume, then it is a magnetovolume effect. On the other hand, as sensor, if you actually change the length and changes happen in the magnetization, that is called Villari effect. Matteucci effect is if you actually twist a material, a magnetostrictive material, and you see a change in magnetization. And Nagoka-Honda effect is just the reverse of magnetovolume effect, where to the change of volume, there is a change in magnetic field that happens in the system. Now, once again, you can see very similar constitutive relationship, that in the first case, the application of magnetic field is creating strain, and in the second case, the application of stress creates this change in the magnetization in the system. So these are the two direct effect and the reverse effect, which are the Joule effect and Villari effect respectively. A lot of applications are there, like in vibration control, noise control, machine tools, servo valves, hybrid motors, sonar devices, ultrasonic cleaning, welding. There are a lot of applications. One of the applications is in terms of actuator development, like Turfenol D rods. These are magnetostrictive rods inside, and you change the current around it, and the piston starts to work, so that you can develop a solenoid type of an application. I will show you one of the applications for crawling. So you can see that how you can move inside a pipe, for example, and inspect the pipe. So this is the earthworm type of a system. and you can increase or decrease the speed because it is magnetic field. So by quickly reversing it, you should be able to increase or decrease the speed. So these are some of the applications of the system, of the magnetostrictive system. Next, I will come to smart muscles based on shape memory alloys and electroactive polymers. Now, what is a shape memory effect? In the shape memory effect, what you have is a temperature change, and this temperature change, for example, a high temperature phase is austenite, and you cool it, you come to a low temperature martensite phase, and then you deform the material, then it goes to low temperature martensite phase, but with a detwined system, and then you apply the heat, it will once again go back to its austenite system. So it can memorize the shape. So for example, you are here, and then you are cooling it, and then you are doing some straining on it, and then once again you are heating it, it will go back to the austenite state. So that is it, and it can be one way, it can be two way. One way it can only remember the parent shape, and two way if it can remember both the shapes in austenite and martensite states. Now there are different materials. For example, gold cadmium alloy is one of them, copper, zinc, aluminum, copper, aluminum, nickel. And it's mostly the nickel titanium that we use, and it was first discovered in the Naval Ordnance Lab of US. So as you can see, this is the high energy state or the austenite state where it is a BCC stage, and this is the low energy face centered cubic martensite state. So essentially, the whole system moves between these two crystal structures. And you can get it in different forms like wear forms or coil spring forms, etc. And it shows a very large actuation strain, something like 10,000 parts per million. Compare it with our muscle, it is quite close to human muscles. That's why these are called artificial muscles. So this slide actually shows the entire generation of the shape memory effect. So let's say if you start from here, if you apply stress on the material, the material is going to get deformed initially elastically, and then like a plastic deformation. And beyond a certain point, if you withdraw the stress, this deformation is plastic. Now you start to heat it, you would see this deformation is vanishing. And finally, at the austenite state, it would become zero. And then if you cool it, there is no further change, and it comes to a twine martensite state. Once again, if you stress it, it will go to detwine martensite phase and complete the cycle. Now, sometimes we do not bring the stress into picture. Simply under the austenite state itself, we actually reverse the stress. We do not bring the temperature into picture, and then it is called a super elasticity effect of the system. There are various applications we have developed, like in deployable structures, in actuators, in stents that is already used for biological, for example, heart surgeries, etc. And then in civil structures like reinforcements and beams, and also in composites for damaging, repairing patches, etc. So this is one of the example of SMA actuated prosthetic hand system. You can see that how you can control the movement of the hand, and thus you can change the the gripping capacity of the system. This is one of the sensors that we have developed for General Motors. Here we have actually used the SMA as a sensor. Between two electrodes, there are these SMA wires which can control these micro switches. So as the stylus moves, it goes from one pair to the other pair. So accordingly, this A gets actuated and then B gets actuated. So there is a actuation signal repeatedly of AB, AB, AB. And based on that, you can actually infer how the rotation is taking place, because this angle is already known to you. So this is one of the things that I have discussed in one of our paper in sensors and transducers. Now, one of the applications is in actuator, and this is a two-link actuation system. Here, by using the SMA wear as muscle wear, you can actually change the shape of the tooling so that you can change the position of the system. So this is a tooling mechanism system. And this is there in Journal of Mechanical Design, and this has been covered. You can see, you can draw a figure of 8 by using this actuator system. And what will be the corresponding voltage level, etc. These are all we have been able to figure it out. Now, there are certain space applications of SMA, for example, in terms of these kind of holding systems or cracking things, or also for antenna systems that we have developed. So the advantage of SMAs is that its strain, free strain is very, very high. That means you can generate a large deformation. And also its force is also quite high because it is metallic system. But its bandwidth is low, so it works slowly. If you want to work faster, you have to use piezoelectric or PVDF type of materials. One last group of material I want to talk about is electroactive polymers. In this case, it's a polymeric system which responds to pH or magnetic field or light. And if it is related to electrical input, then we call it electroactive polymer. If it is any other non-electrical input, then we call it simply active polymers. You can see here that a UV light and a white light combination, how it can create a change of deformations between a bent state or a cis conformation and a straight phase or a trans conformation. And thus you can have a light actuated motion of a system. Now, once again, this has been observed long before 1880 by Ron Zane in one of the experiments, that a rubber band actually is showing this kind of a deformation. But it's only 2010 that Keplinger and people have understood the mechanism. And what it is found out is that there is a pull-in voltage beyond which there is an instability that develops in the system, and the dipoles start to attract each other. So he has been able to develop around this unstable point, different kinds of hinges, and thus he has developed different types of 3D applications of electrode-free charge control deformation of a system. The inspiration for electroactive polymers came from initially a particular resin called Carnauba wax, which is naturally available from a type of palm tree. And then later on, people have actually used different types of polymers and made composites out of it, most importantly, Osada and Kisses. And thus, all these robots that you can see, motor-based robots today, they could be converted to muscle-based system. Now, in order to develop a muscle-based system, you need to always have a pair of muscles, which is called agonist and antagonist. That means one of them will push, whereas one of them will pull, whereas the other one is going to actually relax. So it is pulling and relaxing combination. That's what is going to happen. I'll show you the application of such a system. You can see it here, that how by combination of an agonist-antagonist action, you can generate a different type of motions. As you can see that in the background, this is happening, the pulling and relaxing from both the sides. And that is creating in the front side this kind of a motion. And you can see the endpoint trajectory. You can develop different trajectories, and at different speed, you can actually execute it. Now, such a thing is also used for in Switzerland. There is a electroactive polymer-based blimp system, which is used for artificial fish. And you can see it here that this is where, is this electroactive polymers there. And both in the tail as well as in the fin. And I'll just show you that how it finally works. So to look at the system. Well, the video is a little longish, but you can see somewhere here, you can see that how this whole thing works. So you can see that how this whole thing expands and contracts. Okay, so at this particular point. So this is one of the applications. And there are different types you can develop using electrostatic papers, dielectric EAPs, ionic polymer gels, then IPMCs, which we are using mostly, conductive polymers, and even CNTs. Now, electronic EAPs need actually really high activation voltage, whereas ionic EAPs need low activation voltage. The fish example that I've shown you, that needs low driving voltage, but they have relatively slow response time, whereas electronic EAPs are faster, but they need higher voltage. And IPMCs, the structure has two combinations. One is whatever is used in your Teflon-based, non-stick pans, similar to that, the PTFEs, and the other group is the sulfonate group. So the PTFE groups gives it the strength, and the sulfonate groups gives it the polarity. As a result, it can deform, and you can deform by placing the cations and anions. You can deform it in bidirectional way. So you can develop quite a large deformation in such a system in the IPMCs. And by changing these electrode patterns, you can have a concave and convex deformation both. So you can develop a double curvature in such a system. This we have used in single link manipulator, multi-link grippers, for vibration control, for 4-bar manipulator, many applications. Dust wipers, for example, and this is for all space applications. Gripper I have already shown you. So there are quite a bit of applications. Now I would now like to talk about some future directions. One is in terms of metamaterials, another is programmable materials, and the other group is microstructured auxetic materials. Now, what are these metamaterials in the smart material domain? This is some of the newest things. So here, what you can do is that you can develop a repetitive units of systems in which it will be essentially a mass inside a mass, and thus there will be repeated units. Now, these are called metamaterials, which is having such repeated units, and you can make it actually electromagnetic and even piezoelectric in nature, each one of them. And by controlling the frequency of each one of them, you can actually generate a sort of a negative inertia under certain frequency bands. So you can see here that there are these repeated units there, and each unit is having a mass inside and a piezoelectric coupling. This theta is a piezoelectric coupled system. And this entire system, if you look at it in different frequency bandwidth, what you will be astonished to see is that in certain frequency bands, there is a drop in terms of the wave number, in the sense that there will be a complete attenuation. That means no wave will be able to pass through such a system. So it will work like a selective, attenuator. So this is one of the metamaterial units that we are working on, and you will see in one of our papers, of recent papers on Journal of Intelligent Material Systems, we have reported. The other group is that, can you develop programming inside such metamaterials that can create amazing properties in it? Imagine that you have a honeycomb system and you have piezoelectric patches inside this honeycomb system. And through that, you can actually control the angles of the honeycomb system. So you can develop unimorphs, you can develop bimorphs, you can develop systems which will be voltage dependent dominant or load dominant systems. But essentially what you are going to get is this kind of a system. Let us say for a unimorph system with positive voltage, as you can see here that these red lines are going upwards and blue line is for low voltage. So as you are increasing the voltage, you are actually increasing the modulus of elasticity by several orders of magnitude, from 10 to the power minus 8 to 10 to the power minus 4, 10 to the power minus 2. I mean, it is unbelievable. You can make something very, very rigid to soft. And again, By reversing the voltage, you can generate just the other way. You can develop a very soft system out of it. So this is something that we have reported in one of our paper in International Journal of Solids and Structures. So this entire trick is that you are actually playing with this angle. By using piezoelectric material, you are changing these angles, and as you are changing the angle of a honeycomb, you can change the modulus of elasticity of the system drastically. So this is some of the changes that you can do, like you can increase E1, you can increase E2s and decrease by changing the voltage, etc. And there are situations which are voltage dominant and situations which are stress dominant. I will come to the last of our works, which is on scientific reports of Nature. It was reported, that is how you can make a dynamic hourglass-shaped lattice metastructures. Now, you see, the metastructures are something that can be used in terms of the curvature change. Something like a system which is having, let us say, a dome-shaped curvature. Okay, so by using a kind of a auxetic material, you can control the dome-like behavior of the synclastic curvature of the system. Now, this kind of a thing was known to people for a very, very long time. For example, if you look at Taj Mahal, if you look at many of the domes, people knew that how the compression can develop a system which can withstand the tension, essentially by developing compression inside. So essentially, by giving a kind of a curvature shape, you can withstand the tension. Now, however, these systems are not dynamic in nature. That means you develop it once and it is fixed in that curvature shape. But what we have developed is that by developing some kind of a auxetic or pattern system inside a lattice, you can actually control the behavior of the lattice. You can control the curvature. So here are different types of auxetic structures. You can see that these are domru-like structures. So something can be homogeneous, something can be honeycomb, something can be reverse honeycomb. You can have all variants of it. And what is the effect of these variations in the lattices? That you can get different types of load versus deformation characteristics. In some cases, it works like a fluid, almost plastic zones, and then it stiffens. In some cases, it works in a very, very stiff manner. So all these things you can do by changing the properties of these, these kinds of the curvatures inside these patterned lattices. And this, as I told you, that this can be done with the help of piezoelectric material also. So this is all that that are there. And if you talk about nature, I want to show you what nature has been able to develop. So this is an antenna system that nature has been able to develop. And of course, this is not able to play that this leaf system. There are certain plants in Assam, it is available. They can change their shape by actually changing these two winglets with respect to the sun's ray. And that is something that is an ultimate in terms of a shape control. So whether someday our structures can be able to develop it, we do not know, but this is something we wish to achieve. Now, I want to acknowledge many of my former PhD students who are faculty at different IITs now, Dr. S. Kalra, Mr. Sandeepan Adhikari, Dr. B.S. Munjal is one of our partner for this work for a long time, Dr. Milind Mahajan, Professor Hiroaki Agatsuma, Dr. Tanmay Mukhopadhyay, Dr. Arnab Banerjee in IIT Delhi now. And of course, I have not mentioned, but I should have had Mr. A.C. Mathur. He has helped us a lot in the SMA-related materials. So all these slides that I have presented is by the joint effort of the research scholars of SMSS lab with all the field elements. This is where I would like to stop, and I'd like to get any questions from you. Thank you.
Thank you, Professor Vishak Bhattacharya, for such a wonderful talk. And I'm sure all the participants must have enjoyed as you took us through a journey of actuators and sensors. So the forum is open now for question and answer session. Are there any questions from participants? Hari, can you even check on YouTube platform?
There are no questions on YouTube.
Okay. So, sir, I have a question. I myself work in magnetic fluids because you had mentioned electrorheological fluids and magnetorheological fluids.
Yeah.
So, what are what can be the space applications based on these magnetorheological fluids? And
Yeah, one of the
also used as in soft robotics.
Both in soft robotics as well as in space applications, remote arm manipulators, for example, there you need to move a system. Okay, so in order to do that, you need to do certain torque transfer from system A to system B. Now, by using a magnetorheological fluid-based system, you can actually make the joint to be rigid so that the torque transfer can happen. And when the torque transfer has happened and the rotation has taken place, then again you fluidize the system so that whatever is the disturbance on the main structure that is happening is not going to get transmitted to the system. So thus you can actually play with it. And similar thing we also play in soft robotics.
Sir, I have one more question. I mean, how one can actually make combination of origami and shape memory alloy?
Yeah, we can. In fact, one of our work right now, which is sponsored by Space Technology Cell, we are working on, is actually a origami antenna system. So this kind of antenna systems, they are actually folded essentially, and along the folded lines, like Professor Upadhyay has shown that he has developed a cut and joint systems, but in this case, it is piezoelectric material or the inflation by compressed air. But in our case, along these joints, we actually keep the SMA wear. So as you are applying current, the SMA wear applies the force on the system. And that can actually help in terms of unfolding the system. So we are currently working on this project.
So are there any questions from participants?
I have a question or rather like a request for a suggestion. Sir, like, are there any publications or somewhere where we could keep reading about this other than research papers? Like, are there any journals or some place where you could suggest where they speak about this?
Well, one of the things that I would suggest is that IIT Kanpur, if you go through the directions of IIT Kanpur, we have devoted one full book on smart materials. So please, its e-copy is freely available. So please go through the directions. Direction is the IIT Kanpur's yearly, once or twice we publish all the research compiled together. And very nicely there, all the applications of smart materials are given.
Thank you, sir.
So with that, we move to the last part of this session. I thank all the participants who have joined from Zoom and YouTube and who have been attending all the sessions right from 2 o'clock. And I thank again Professor Bishak Bhattacharya for giving us very insightful talk on smart materials, actuators and sensors. So we will be joining tomorrow, and tomorrow we will be having again 3 talks, 2 on the composite materials and 1 talk will be on the manufacturing aspects. Mathur sir, would you like to add something? Sir, your mic is muted. Mathur sir, your mic is muted.
Yeah. There are 3 talks, 2 on composites and 1 on manufacturing aspects tomorrow. And the second talk, composite, is by Dr. R.M. Vijay Rao. Still, he is not through with his Zoom system on the laptop. So it appears to be doubtful. He says, I will record my talk and send it on WhatsApp. So maybe we may have 2 talks tomorrow. Third one, I'm not sure. Okay, so request all the participants to attend in time. We'll start at 2 o'clock. And let me also thank Dr. Bishak Bhattacharya for sparing his valuable time, more than an hour, and shared his experiences with us. It was a quite knowledgeable topic. Thank you.
Thank you, Mathur sir.
Thank you, sir.
Yeah. Okay.
Hari, would you like to stop streaming?